Right now, as you listen to these words, a single second is passing on your watch. In that second, 9,192,631,770 oscillations of a cesium-133 atom have occurred inside a laboratory in Boulder, Colorado. This is not an approximation. This is not a round number chosen for convenience. This is the exact, internationally agreed upon definition of 1 second of time. A definition so precise that if every cesium atom on Earth were counted and measured, they would all vibrate at this identical frequency, a cosmic heartbeat that humanity has chosen as the universal metronome of existence. And yet, in that same second on your watch, a particle called a muon has lived its entire life. Born in the upper atmosphere when a cosmic ray strikes a nitrogen molecule, this subatomic traveller exists for approximately 2.2 microseconds in its own reference frame, a lifespan so brief that it should decay long before reaching the ground. It does not. It arrives at sea level having experienced a complete existence, from creation to annihilation, in what your watch registered as a fraction of a moment. The muon did not cheat physics. The muon experienced time differently than you did. At this same instant, somewhere in the constellation Cygnus, approximately 6,000 light-years from Earth, a boundary exists around a stellar mass black hole, where the fabric of space-time has been so severely warped that what you just experienced as 1 second would register as decades, perhaps centuries, for anything falling past that threshold. Not metaphorically, not poetically, mathematically, measurably, undeniably. A second outside is an epoch inside. The same word, the same unit, the same tick of an imagined cosmic clock means something so different in these three contexts that calling them all seconds borders on absurdity. Here is what will shatter everything you think you understand about time. A second is not a thing that exists in nature. A second is a human invention, a convenience, a linguistic agreement between billions of people who needed to coordinate their activities on a spinning rock. The universe has no seconds. The universe has no minutes, no hours, no days. The universe has only the relentless asymmetric unfolding of events from one state to another, and the rate at which this unfolding occurs depends entirely on where you are, how fast you are moving, and how much mass is warping the space-time around you. You're moving through multiple versions of a second right now, in this very moment, without noticing. The crown of your head is aging faster than your feet. The blood flowing through your arteries experiences time differently than the blood returning through your veins. These differences are so microscopically small that no human could perceive them, but they are real, they are measurable, and they accumulate over a lifetime into effects that modern physics must account for, or our global navigation systems would drift into uselessness within hours. If you want to discover how a single word can mean such radically different things in different places, and enjoy this type of exploration of reality's hidden architecture, then please consider liking and subscribing. It truly helps more than you know. Are you ready? Let's begin. The story of the second begins in Babylon, approximately 4,000 years ago, in the mud brick ziggurats that dotted the Fertile Crescent between the Tigris and Euphrates rivers. The Babylonians inherited a number system from the Sumerians, a system built not on 10s but on 60s. Why 60? Because 60 is extraordinarily divisible. You can split it evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. For a civilization conducting trade, measuring grain, and tracking the movements of celestial bodies, this flexibility was computational gold. They divided the circle into 360 degrees. They divided each degree into 60 minutes of arc. They divided each minute into 60 seconds of arc. The words minute and second entered human consciousness, not as measurements of time, but as measurements of angle, of the slow wheeling of stars across the night sky. The ancient Egyptians contributed something else. They looked at their sundials and divided the daylight hours into 12 parts, and the night hours into 12 parts, giving the day 24 segments. But these segments stretched and compressed with the seasons. A summer hour in Alexandria was literally longer than a winter hour. The 12 portions of daylight had to cover more ground when the sun lingered. The concept of equal hours, hours that remained the same length regardless of the season, emerged only later, when mechanical clocks began ticking in medieval European monasteries. Picture a Benedictine monk in the 13th century, standing in a cold stone corridor, listening to the steady drip of a water clock. His day is divided into canonical hours: matins, lauds, prime, terce, sext, none, vespers, compline, and his entire existence orbits these prayer times like planets around a sun. The water clock tells him when to pray, when to eat, when to sleep. But the water clock is imprecise. It runs faster in summer when the water is warmer and flows more freely. It runs slower in winter when ice threatens to stop it entirely. The monk does not know that he is living in a world where time itself seems to shift with the temperature, where a second in July is literally shorter than a second in January according to his measuring device. By the 14th century, mechanical clocks with escapements began appearing in European town squares. These devices used the controlled release of potential energy, falling weights regulated by gear trains, to create a steady tick. For the first time in human history, people could hear time passing. The tick of a clock became the sound of seconds being born and dying one after another, a mechanical heartbeat that replaced the organic rhythms of sundials and water clocks. But here is what those medieval clockmakers did not understand. Every clock they built was lying to them. Not because the mechanisms were imprecise, though they were, but because the very concept they were trying to measure does not exist in the way they imagined. They believed that a second in Paris was identical to a second in Rome, was identical to a second in London. They believed that time flowed like a river at a constant rate everywhere in the universe, carrying all things forward at the same speed. This belief would dominate human thinking for the next 5 centuries, until a patent clerk in Bern demonstrated that it was profoundly, fundamentally wrong. The cesium-133 atom is unremarkable in most respects. It is a soft, silvery gold metal that reacts violently with water and must be stored under mineral oil to prevent it from bursting into flame upon contact with moisture in the air. It has 55 protons in its nucleus, making it the heaviest stable alkali metal. It melts at just 28 degrees Celsius, slightly below human body temperature, which means that if you held a piece of pure cesium in your palm, it would liquefy from the heat of your hand moments before reacting with the moisture in your skin. But cesium-133 has one extraordinary property that elevated it from chemical curiosity to the fundamental definition of time itself. When cesium-133 atoms are exposed to microwave radiation at exactly the right frequency, their outermost electrons flip between 2 specific energy states. This transition occurs at a frequency so stable, so reproducible, so immune to outside interference that it might as well be carved into the structure of the universe itself. The electron does not wobble. The electron does not drift. The electron flips at precisely 9,192,631,770 cycles per second, and it does this whether the atom is in Boulder, Colorado, or Tokyo, Japan, or on a satellite orbiting the Earth. In 1967, the 13th General Conference on Weights and Measures gathered in Paris and made a decision that rewrote human civilization's relationship with time. They declared that 1 second was no longer defined by the rotation of the Earth or the orbit of the Earth around the Sun. 1 second was now defined as the duration of exactly 9,192,631,770 periods of the radiation corresponding to the transition between the 2 hyperfine levels of the ground state of the cesium-133 atom. This definition seems absurdly specific until you understand why it was necessary. The Earth is not a reliable clock. Our planet's rotation is slowing down due to tidal interactions with the Moon, causing the length of a day to increase by approximately 1.4 milliseconds per century. Earthquakes shift mass within the Earth, changing its moment of inertia and subtly altering its rotation rate. The planet wobbles on its axis like a poorly thrown football. The orbit around the Sun is not perfectly circular but elliptical, causing the length of a solar day to vary throughout the year. For millennia, none of this mattered. Human activities did not require precision to the millionth of a second. But by the mid-20th century, everything had changed. Navigation satellites needed to agree on time to within billionths of a second, or position calculations would be wrong by meters, then kilometers, then catastrophically useless. Power grids needed synchronization to prevent cascading failures. Financial markets needed timestamps that could be trusted across continents. The world needed a definition of the second that did not depend on a spinning, wobbling, gradually slowing planet. Cesium gave us that definition, and cesium revealed something else, something unsettling about the nature of the second we thought we understood. The National Institute of Standards and Technology maintains a facility in Boulder, Colorado, at an elevation of approximately 1,250 meters above sea level. Inside this facility sits one of the most precise atomic clocks ever constructed, a device called NIST F2 that would lose or gain no more than 1 second if it ran continuously for 300 million years. This is precision beyond human intuition. This is precision that borders on the philosophical. In 2010, physicists at NIST conducted an experiment that demonstrated something about time that Einstein had predicted a century earlier, but that humans had never directly observed in such a mundane context. They took 2 identical atomic clocks, placed one on a laboratory bench, and raised the other by just 33 centimeters, roughly the height of a typical stair-step. Then they let both clocks run and compared their readings. The clock that was 33 centimeters higher ran faster, not because it was broken, not because of temperature differences or electromagnetic interference. The higher clock experienced time passing at a genuinely faster rate because it was further from Earth's gravitational centre. The difference was absurdly small, roughly 90 billionths of a second per 79 years. But it was real, it was measurable, and it was exactly what Einstein's general theory of relativity had predicted. This is gravitational time dilation, and it means that the second ticking on your watch is not the same second ticking on a watch at the top of a tall building. The second experienced by a pilot at cruising altitude is not the same second experienced by a passenger waiting at the gate. The second passing in the basement of a hospital is not the same second passing in the penthouse above it. These differences are so small that they could never be perceived by human senses, but they exist. They accumulate. And when you multiply them by the mass of objects far denser than Earth, they become the dominant feature of the universe. Consider a neutron star. When a massive star exhausts its nuclear fuel and collapses, it can leave behind a core so dense that a teaspoon of its material would weigh approximately 6 billion tons. This core is typically only about 20 kilometers in diameter, roughly the size of a city, yet it contains more mass than the Sun. The gravitational field at the surface of a neutron star is approximately 200 billion times stronger than the gravitational field at Earth's surface. At this surface, time slows dramatically. A clock placed on a neutron star would run noticeably slower than an identical clock in deep space, far from any gravitational influence. Not because the clock is broken, not because the mechanism has been affected by the extreme conditions. Time itself, the fundamental rate at which events unfold, is genuinely slower at the surface of a neutron star than it is in the void between galaxies. If you could somehow survive standing on a neutron star surface, you cannot. You would be crushed into a thin film of atoms by the gravitational gradient alone. And you looked up at the stars above you, you would see them moving faster than they should. Their orbits would appear accelerated, their lifespans would seem compressed. Not because the stars are misbehaving, but because you are experiencing time more slowly than they are. A second on your watch would correspond to more than a second passing in the distant universe. But neutron stars are merely the opening act. The true extremes of gravitational time dilation occur around black holes, objects so dense that not even light can escape their gravitational grasp. And here, the second, that convenient human unit we thought we understood, becomes something unrecognizable. The event horizon of a black hole is not a physical surface. It is a boundary, a mathematical threshold, a point of no return beyond which escape becomes impossible. Nothing special happens at the event horizon itself. An astronaut falling through would notice nothing unusual at the moment of crossing, would detect no wall, no barrier, no sudden change in local conditions. But from the perspective of an observer watching from a safe distance, something extraordinary occurs. Picture a clock falling toward a black hole. As it approaches the event horizon, its ticking appears to slow from the perspective of the distant observer. The closer it gets, the slower it seems to tick. Not because the clock is malfunctioning, but because the photons carrying information about each tick are climbing out of an increasingly deep gravitational well, losing energy, stretching to longer wavelengths, arriving less frequently. At the event horizon itself, time appears to stop. The distant observer would see the clock freeze, its display eternally showing the same instant, the moment of crossing preserved forever in the photons that barely escaped before the clock passed through. From the perspective of the distant observer, the clock takes an infinite amount of time to cross the event horizon. From the perspective of the clock itself, from the perspective of any unfortunate astronaut clinging to that clock, the crossing happens in a finite time, perhaps mere milliseconds for a stellar mass black hole, perhaps hours for a supermassive one. This is not a paradox. This is the nature of time in curved space-time. The second experienced by the falling clock and the second experienced by the distant observer are not the same second. They are not even comparable in any straightforward way. The word simultaneous loses meaning across these gravitational distances. Asking what the distant observer's clock reads at the same moment the falling clock crosses the horizon is not a question physics can answer. There is no universal now that connects these two reference frames. Inside the event horizon, the situation becomes stranger still. The mathematics of general relativity reveals that within the black hole, the roles of space and time become interchanged in a sense that defies everyday intuition. The singularity at the centre is not a place in space that you could avoid if you moved cleverly. The singularity is a moment in time, specifically your future. Once inside the event horizon, all possible paths through space-time lead toward the singularity, just as all possible paths outside the black hole lead toward the future. You cannot avoid the singularity any more than you can avoid tomorrow. How long does this journey take? The answer depends entirely on the mass of the black hole. For a stellar mass black hole formed from a collapsed star, the journey from event horizon to singularity might take mere milliseconds of proper time. The time as experienced by the infalling observer. For the supermassive black holes at the centres of galaxies, which contain millions or billions of solar masses, the journey could take hours. During this time, the infalling observer would experience time normally by their own internal reckoning. Their heart would beat, their thoughts would progress, their watch would tick. But outside, in the universe they left behind, civilizations would rise and fall, stars would complete their life cycles. Billions of years could pass between the moment the observer crossed the event horizon and the moment they reached the singularity, if moment has any meaning when comparing these two incomparable reference frames. The second inside the black hole and the second outside the black hole are separated by more than distance. They are separated by the fundamental structure of space-time itself, by a curvature so extreme that comparing them directly becomes meaningless. This is what Einstein's equations demand. This is what the mathematics insists upon. This is the reality that emerges when you take seriously the proposition that gravity is not a force pulling objects together, but a curvature in the fabric of space and time itself. Now consider something far smaller than a black hole, far more ephemeral than a neutron star. Consider the muon. Muons are elementary particles, members of the lepton family along with electrons and neutrinos. They carry the same electric charge as electrons but are approximately 207 times more massive. They are unstable, decaying into an electron and two neutrinos with a half-life of approximately 2.2 microseconds. This half-life is not variable. It is not affected by temperature, pressure, or chemical environment. It is an intrinsic property of the muon itself, written into the laws of particle physics. Cosmic rays, high-energy particles originating from supernovae, active galactic nuclei and other violent cosmic events, constantly bombard Earth's upper atmosphere. When a cosmic ray proton strikes a nitrogen or oxygen nucleus at an altitude of approximately 15 kilometers, it produces a shower of secondary particles, including pions. These pions decay almost immediately into muons. The muons continue downward toward Earth's surface at velocities approaching the speed of light. Here is the problem. Even travelling at 99.5% of the speed of light, a muon created at 15 kilometers altitude should only travel approximately 660 meters before decaying. The mathematics is straightforward. 2.2 microseconds times 95 times 300,000 kilometers per second gives roughly 660 meters of travel distance. Yet muons created at the top of the atmosphere reach sea level in enormous quantities. They pass through your body at a rate of approximately 1 muon per square centimetre per minute right now as you listen to these words. How do they survive the journey? The answer is time dilation. Not gravitational time dilation, but velocity-based time dilation, the phenomenon Einstein predicted in his 1905 special theory of relativity. From the muon's perspective, it lives for 2.2 microseconds. It is born in a collision, it races downward, it decays into lighter particles. A brief, complete existence. But from the perspective of a detector on Earth's surface, the muon's internal clock is running slow because the muon is moving at such extreme velocity relative to the detector. At 99.5% of the speed of light, the time dilation factor, called gamma, is approximately 10. This means that while the muon experiences 2.2 microseconds of proper time, the Earth-based detector observes the muon existing for approximately 22 microseconds. 22 microseconds at 99.5% of light speed gives 6.6 kilometers of travel distance, easily enough to reach the surface from 15 kilometers altitude when combined with statistical distribution effects. The muon is not cheating physics. The muon is demonstrating that a second is not a universal constant. The second experienced by the muon and the second experienced by the detector are different seconds. They are both equally real. They are both equally valid measures of the passage of time, and they disagree profoundly on how long the muon lived. From the muon's frame of reference, there is a complementary explanation that preserves the same physics with different emphasis. The muon sees itself at rest and sees the Earth rushing upward toward it at 99.5% of light speed. From this perspective, the distance between the muon and Earth's surface is length contracted, compressed by the same factor of 10. The 15-kilometre journey becomes a 1.5-kilometre journey in the muon's reference frame. At near light speed, 1.5 kilometres takes only a few microseconds to traverse. The muon doesn't need to live longer, it just doesn't have as far to travel. Both explanations are correct. Both are valid descriptions of the same physical reality. The apparent contradiction, one observer says the muon lived longer, the other says the distance was shorter, resolves because time and space are not separate, independent quantities. They are woven together into a unified fabric called space-time, and different observers moving at different velocities slice through this fabric at different angles, disagreeing on what counts as space and what counts as time, while agreeing perfectly on the space-time interval connecting events. This leads to a peculiar realization about your own existence in this very moment. You're not moving through time at a constant rate. You never have been. You never will be. As you sit or stand or lie down listening to these words, different parts of your body are experiencing time at different rates. Your head, being further from Earth's centre than your feet, exists in a region of slightly weaker gravity and therefore experiences time passing slightly faster. Over a typical human lifespan of 80 years, this means your head has aged approximately 90 billionths of a second more than your feet. This is not metaphor. This is measurement. The blood flowing through your arteries is moving faster than the blood returning through your veins due to the mechanics of your cardiovascular system. Moving objects experience time dilation relative to stationary ones. The blood rushing from your heart toward your fingertips is aging more slowly than the blood drifting back. The difference is so small that it disappears into the noise of measurement uncertainty, but it exists. Physics demands it. If you have ever flown on an airplane, you have accumulated tiny fractions of microseconds of time difference relative to people who stayed on the ground. Commercial aircraft typically cruise at around 900 kilometers per hour and at altitudes around 10,000 meters. At these speeds and heights, two effects compete. The velocity-based time dilation, special relativistic, slows your clock relative to someone on the ground, while the gravitational time dilation, general relativistic, speeds it up because you are further from Earth's centre. For typical commercial flights, the gravitational effect wins slightly, meaning you age slightly faster while flying than if you'd stayed home. These effects were directly measured in 1971 in an experiment conducted by physicists Joseph Hafele and Richard Keating. They flew cesium atomic clocks around the world on commercial airliners, once eastward, once westward, and compared the flown clocks to identical clocks that remained at the United States Naval Observatory in Washington, D.C. The eastward flying clock lost 59 nanoseconds compared to the stationary clock. The westward flying clock gained 273 nanoseconds. Both results agreed with Einstein's predictions to within experimental uncertainty. Nanoseconds. Billionths of seconds. amounts so small that they would never matter for any human activity not involving atomic precision. And yet these nanoseconds prove something profound. The second on your watch is parochial. It is local. It is specific to your particular trajectory through space-time and does not represent any universal truth about the rate at which events unfold. The global positioning system that guides your car, your phone, your airplane cannot function without accounting for these effects. Each GPS satellite carries an atomic clock that is synchronized with clocks on Earth's surface. The satellites orbit at approximately 2,200 kilometers altitude, moving at approximately 14,000 kilometers per hour. At these altitudes and velocities, relativistic effects are significant enough to cause measurable errors in position calculations. The satellite's clocks run faster than ground-based clocks due to gravitational time dilation, approximately 45.9 microseconds per day faster. They run slower due to velocity-based time dilation, approximately 7.2 microseconds per day slower. The net effect is that satellite clocks gain approximately 38.7 microseconds per day relative to clocks on Earth's surface. 38.7 microseconds, less than 40 millionths of a second per day. Utterly imperceptible to human senses, and if the GPS system did not correct for this difference, positional errors would accumulate at a rate of approximately 11 kilometers per day. Within a week, your GPS would be off by nearly 80 kilometers. Within a month, your navigation system would be useless. Every time your phone calculates your position, every time your car guides you through an unfamiliar city, every time an airplane descends through fog toward a runway it cannot see, Einstein's relativity is being confirmed. The satellites are not running on Earth seconds. The satellites are running on satellite seconds. Seconds that tick at a different rate than the seconds in your pocket, and the entire system works only because we understand that these are different things with the same name. This brings us to a question that has troubled physicists and philosophers for centuries. If a second is not the same everywhere, if time itself runs at different rates in different places and for different observers, then what is time? Isaac Newton believed he knew the answer. In his Principia Mathematica, published in 1687, Newton wrote, "Absolute, true and mathematical time, of itself and from its own nature, flows equably without relation to anything external." For Newton, time was a stage upon which events unfolded, a constant background against which motion and change occurred. Time was the same everywhere, always, for everyone. A second in London was identical to a second in Beijing, was identical to a second on the surface of the sun, was identical to a second at the edge of the universe. This view dominated physics for more than 2 centuries. It seemed obviously correct. It matched human intuition. It worked beautifully for calculating the motions of cannonballs, planets, and pendulums. And it was wrong. Einstein's special theory of relativity, published in 1905, demonstrated that Newton's absolute time was an illusion created by the extremely slow velocities at which humans normally move. At walking speeds, at car speeds, even at rocket speeds, the effects of time dilation are so small that they are undetectable by ordinary means. Only when objects approach the speed of light do the differences become obvious. Newton was not wrong about everyday experience. He was wrong about the fundamental nature of reality. The speed of light is approximately 299,192 kilometers per second. Nothing with mass can reach this speed. Nothing with mass can exceed it. This is not merely an engineering limitation that might be overcome with sufficient technology. This is a fundamental property of spacetime itself. As an object with mass accelerates toward the speed of light, the energy required to accelerate it further increases without bound. At the speed of light, infinite energy would be required. The speed of light is not a barrier to be broken. It is a boundary woven into the structure of existence. But within this limitation lies a profound freedom. Time is not fixed. Space is not fixed. They trade off against each other, compressing and stretching depending on velocity and gravitational field, preserving only the space-time interval between events, while allowing radically different decompositions into temporal and spatial components. The muon lives 2.2 microseconds by its own clock and 22 microseconds by yours. Both are correct. The astronaut falling into a black hole experiences hours while the universe outside ages billions of years. Both are correct. The clock on the mountaintop runs faster than the clock in the valley. Both are correct. There is no arbitrator. No cosmic referee declaring that 1 second is the real second and the others are illusions. They are all real, they are all seconds, and they are all different. Consider what this means for a concept as fundamental as now. When you say that something is happening right now on the Sun, you're using language imprecisely. Light takes approximately 8 minutes and 20 seconds to travel from the Sun to Earth. Any event you observe happening on the Sun actually occurred 8 minutes ago by the time you see it. But even this corrected conception of now, an event happening on the Sun right now, being defined as an event you will see in 8 minutes, relies on a definition of simultaneity that special relativity reveals as observer-dependent. Imagine two events. A solar flare erupts on the Sun, and at the same moment you drop a penny on Earth. For an observer at rest relative to both events, these events might be simultaneous. They occur at the same coordinate time. But for an observer moving at high velocity relative to both, the events are not simultaneous. Depending on the direction of motion, the moving observer might say the solar flare happened before the penny dropped, or that the penny dropped before the solar flare. Both observers are correct within their own reference frames. There is no absolute answer to which event happened first. This is not a failure of measurement precision. This is a feature of space-time itself. Simultaneity is relative. Now is a local concept that loses meaning when extended across large distances, or between frames moving at significant fractions of the speed of light. The second on your watch and the second on a clock orbiting a black hole are not simply different measurements of the same underlying quantity. They are genuinely different experiences of time, equally valid, equally real, connected only by the mathematical machinery of relativity that relates one observer's measurements to another's. When you speak of a second, you're not speaking of anything that exists independently of who is doing the measuring, where they are, and how they are moving. And yet, despite all of this, cesium-133 atoms still oscillate at the same frequency everywhere. That number, 9,192,631,770, remains constant regardless of where the atom is located or how it is moving. This seems paradoxical until you understand what the statement actually means. The cesium frequency is measured in cycles per second. But whose second? The answer is the proper time of the cesium atom itself. If you're at rest relative to a cesium atom and measure its frequency, you will count 9,192,631,770 cycles per second. If the cesium atom is moving at high velocity relative to you, and you measure its frequency, you will count fewer cycles per second because the atom's clock is running slow relative to yours, but if you calculate what an observer travelling with the atom would measure, you get the same 9,092,630,70. The constancy of the cesium frequency is thus a statement about proper time, about the time experienced by the measuring apparatus in its own rest frame. It is not a statement about cosmic time or absolute time or any universal metronome ticking away behind the scenes. The second defined by cesium is a local second, a second that exists only in the immediate vicinity of the measuring device, a second that changes its relationship to other seconds depending on the geometry of space-time surrounding it. This is the hidden truth buried within that deceptively simple definition from the 1967 conference, when humanity declared that 1 second equals exactly 9,192,631,770 periods of cesium radiation. We were not pinning down an absolute unit of cosmic time. We were declaring what we would mean by second in our local frame, on the surface of our planet, in the gravitational field of our star. A second elsewhere, a second on the surface of Jupiter, a second aboard an interstellar spacecraft, a second near the event horizon of a black hole, is related to our second by the mathematics of relativity, but it is not identical to our second. The muon lives its entire existence in one of our seconds. The traveller near the black hole experiences decades of their proper time in what we call 1 second. Both are using the same word to describe experiences so different that calling them by the same name obscures more than it reveals. The second is not a universal constant. The second is a local convention. This realization carries weight that extends far beyond the theoretical. Consider what it means for navigation, for communication, for the very infrastructure of technological civilization. The global positioning system that guides aircraft to their runways and ambulances to their emergencies depends on a constellation of 31 satellites orbiting Earth at an altitude of approximately 2,200 kilometers. Each satellite carries atomic clocks, cesium and rubidium oscillators of extraordinary precision, and each of those clocks experiences time differently than clocks on the ground. The satellites are moving at roughly 14,000 kilometers per hour relative to Earth's surface. Special relativity tells us that their clocks should run slow compared to ground-based clocks by approximately 7 microseconds per day. But the satellites are also 2,200 kilometers above Earth's surface, farther from the planet's center of mass, experiencing weaker gravity than clocks at sea level. General relativity tells us that their clocks should run fast compared to ground-based clocks by approximately 45 microseconds per day. The two effects work in opposite directions. The gravitational effect dominates, producing a net gain of about 38 microseconds per day, 38 millionths of a second every 24 hours. This sounds inconsequential. It is not. GPS works by measuring the time signals take to travel from multiple satellites to your receiver. Your position is calculated by comparing arrival times with exquisite precision. Light travels approximately 297,792 kilometers per second. In 38 microseconds, light travels about 11 kilometers. If the GPS system did not account for relativistic time differences between orbiting clocks and ground-based clocks, positioning errors would accumulate at roughly 10 kilometers per day. Within a week, the system would be useless for navigation. Within a month, it would tell you that you were in a different city than you actually occupied. The engineers who designed GPS understood this. Before the first operational satellite was launched, they programmed the onboard clocks to run at a slightly different frequency than ground clocks, slow by about 4.465 parts in 10 billion, precisely calibrated to cancel the relativistic effects experienced in orbit. The clocks launched into space already compensating for the fact that they would experience time differently than clocks on the ground. Every time your phone tells you where you are, every time an airplane follows its flight path, every time a missile finds its target, you're witnessing a practical demonstration that the second is not the same everywhere. The technology works because we understand that time passes at different rates in different gravitational potentials and at different velocities, and we adjust for those differences with mathematical precision. This is not physics as abstract theory. This is physics as daily necessity. The second on the satellite and the second on the ground are measurably, functionally, consequentially different, and trillions of dollars of infrastructure depend on accounting for that difference. The particle physics laboratories scattered across the globe offer another window into this strange landscape. At facilities like CERN near Geneva, Fermilab outside Chicago, and the Keck laboratory in Japan, physicists routinely create particles that should not exist long enough to be studied. Consider the tau lepton, a heavier cousin of the electron. The tau has a mean lifetime of approximately 290 femtoseconds in its own rest frame. A femtosecond is 1/quadrillionth of a second, a millionth of a billionth. At rest, a tau particle would travel less than a millimeter before decaying, even if it moved at the speed of light. Yet when taus are created in high-energy collisions and emerge with substantial velocity, they travel measurable distances in the laboratory, leaving tracks in detectors, producing daughter particles that themselves leave tracks. The tau's brief existence is stretched by time dilation, its internal clock running slow relative to the laboratory clock, its femtosecond lifetime becoming long enough for the particle to traverse detector arrays and leave signatures that physicists can analyze. Every experiment involving unstable particles at high energy depends on this effect. The detection of neutrinos from cosmic ray showers, the measurement of strange quark behavior, the search for new physics beyond the standard model, all of these rely on particles living longer in the laboratory frame than they would in their own rest frame. If time dilation were not real, these experiments would produce nothing but confusing noise. Instead, they produce Nobel Prizes. The precision of modern atomic clocks has reached a level where even modest differences in gravitational potential become measurable. Optical lattice clocks, which use atoms trapped in a lattice formed by intersecting laser beams, have achieved fractional uncertainties on the order of 1 part in 10 to the 18th. This means that if you ran such a clock for the entire age of the universe, 14 billion years, it would neither gain nor lose more than a second. At this level of precision, Raising a clock by 1 centimetre, the width of your index finger, produces a detectable difference in clock rate. The clock on the table ticks at a measurably different rate than the clock on the shelf above it. In 2010, researchers at the National Institute of Standards and Technology demonstrated this effect directly. They compared two optical clocks separated by a height of only 33 centimetres, roughly the length of your forearm, and measured a time dilation effect consistent with general relativity's predictions. The lower clock ran slower than the upper clock by about 4 parts in 10 to the 17th. Both clocks were using the same definition of the second. Both were counting the same type of atomic transitions. But they were experiencing different seconds because they occupied different positions in Earth's gravitational field. This has implications that reach into the future of precision measurement. Scientists are now developing clocks that could detect the gravitational influence of small masses placed nearby. A sufficiently precise clock could potentially map underground structures, mineral deposits, aquifers, tunnels, by measuring how local mass concentrations affect the passage of time. The same effect that makes GPS possible could become a tool for geophysical exploration. We would be using time itself as a probe, exploiting the fact that seconds pass at different rates in different places to learn about the distribution of matter beneath our feet. The universe is filled with environments where time dilation reaches extraordinary magnitudes. Neutron stars, the collapsed cores of massive stars that have ended their lives in supernova explosions, pack roughly 1.4 to 2 times the mass of the Sun into a sphere approximately 20 kilometers across. The gravitational field at the surface of such an object is so intense that the escape velocity approaches half the speed of light. A clock on the surface of a neutron star would tick at roughly 70%, the rate of a clock far from any gravitational source. If you somehow communicated with an observer on a neutron star's surface, watching their activities through some hypothetical telescope, you would perceive their movements as occurring at roughly 70% of normal speed. Their seconds would be longer than yours. Their conversations would seem to drag. Their music would play in a lower key. But from their perspective, everything would proceed normally. They would watch you, the distant observer floating in empty space, and perceive you as moving at roughly 1.4 times normal speed. Your seconds would seem shorter than theirs. You would appear to be living life in fast forward, rushing through your days with unseemly haste. Both perceptions would be correct. Neither would be privileged. The asymmetry arises only when someone actually travels between the two locations and brings the time records together for comparison. Black holes represent the extreme case, the logical endpoint of gravitational time dilation. As an object approaches the event horizon of a black hole, the gravitational time dilation factor grows without bound. From the perspective of a distant observer, a falling object never quite reaches the event horizon. Its approach asymptotically slows, its emissions redshifting through the visible spectrum into infrared, into microwave, into radio, finally becoming too weak and too shifted to detect at all. The falling object appears to freeze at the boundary of visibility, an eternal monument to its own infall. But from the perspective of the falling object, nothing unusual happens at the event horizon. The object passes through in finite proper time and continues falling toward the singularity at the centre. The event horizon is a boundary in the distant observer's experience, not in the falling object's experience. Inside the event horizon, the mathematical structure of space-time becomes stranger still. The coordinates that represent time and space trade roles in a certain precise mathematical sense. The singularity at the centre is not a point in space that the falling observer might avoid by steering around it. It is a moment in the future, an inevitable destination in the temporal direction. You cannot escape the singularity for the same reason you cannot escape tomorrow. It lies in your future, and the causal structure of space-time prevents movement backward in time. The supermassive black holes at the centres of galaxies create time dilation effects that persist far from their event horizons. Sagittarius A, the 4 million solar mass black hole at the centre of our own Milky Way galaxy, bends space-time out to distances of billions of kilometres. Stars orbit this monster at velocities reaching 10,000 kilometres per second, close enough that their light shows measurable gravitational redshift. The star S2, which approaches within about 120 astronomical units of Sagittarius A at closest approach, experiences gravitational and velocity-based time dilation that slows its clocks by roughly 1 part in 10,000. relative to clocks here on Earth. If you could watch S2's inhabitants, if it had any, they would appear to live their lives at 99 or 99% of normal speed, nearly indistinguishable from your own rate, but measurably slower. Scale up from Sagittarius A to the ultramassive black holes found in the cores of the largest galaxies. The black hole at the centre of M87, imaged by the Event Horizon Telescope in 2019, contains approximately 6.5 billion solar masses. Its event horizon spans roughly 40 billion kilometres, larger than the orbit of Pluto. TON 618, among the most massive black holes ever detected, may contain as much as 66 billion solar masses. The event horizon of such an object would swallow entire solar systems. Near these leviathans, time dilation effects become macroscopic and dramatic. A planet orbiting just outside the photon sphere of a supermassive black hole, if such a stable orbit could exist, might experience time at a small fraction of the rate experienced by distant observers. A year on such a planet might correspond to centuries or millennia in the wider universe. This is not the realm of pure speculation. The mathematics is well established, confirmed by every experimental test we have been able to devise. The 2015 detection of gravitational waves from merging black holes by LIGO provided yet another confirmation that spacetime behaves exactly as general relativity predicts. The waveforms match theoretical templates calculated from Einstein's equations with exquisite precision. The chirp of gravitational radiation as the black holes spiraled inward, the ring down as the merged black hole settled into its final state, all followed the predictions of a theory that fundamentally depends on the fact that time passes differently in different gravitational environments. The philosophical implications of relativistic time reach into questions about the nature of existence itself. If your second and my second are different, if the second near a black hole and the second far from any gravitational source are related only by mathematical transformation, what does it mean to say that something exists now? The concept of a universal present moment, a cosmic instant that encompasses everything happening in the universe at the same time, is not merely unknown to us. It is incoherent within the framework of modern physics. There is no such thing as the universe now. There are only local nows, personal nows, reference frame dependent nows that cannot be extended into a universal standard without choosing an arbitrary frame of reference and privileging it above all others. Some physicists and philosophers have drawn from this the conclusion that all moments of time are equally real, that the past and the future exist with the same ontological status as the present, that we are embedded in a four-dimensional block universe in which every moment is eternally frozen, and our experience of time passing is a kind of illusion created by the structure of our consciousness. This view, sometimes called eternalism, or the block universe view, remains controversial. Other physicists maintain that there is a genuine becoming, a creative advance of nature, even if the precise boundary between past and future depends on one's reference frame. The debate continues in philosophy journals and conference rooms, with no consensus in sight. What is not controversial is the empirical fact that time is not universal. The second is a local quantity. The definitions we use, the cesium transitions, the SI conventions, the international standards, all refer to time as measured in a particular observer's rest frame, at a particular location in the gravitational landscape of the universe. When we use the word second casually, we are implicitly assuming that we share approximately the same reference frame, the same gravitational environment, the same velocity through space-time. For beings on the surface of one planet, in the gravitational field of one star, moving through the galaxy at roughly the same collective velocity, this assumption is harmless. The differences between your second and your neighbour's second are unmeasurably small, but they are not zero. You're standing in a gravitational field. Your feet are lower than your head. The second at your feet is infinitesimally longer than the second at your head. Your blood cells experience time differently depending on which part of your body they currently occupy. When you climb a flight of stairs, your wristwatch gains infinitesimal nanoseconds relative to the clock you left on the ground floor. When you drive down the highway, your speed induces a time dilation effect that very slightly slows your clock relative to stationary clocks. These effects are far too small to measure with ordinary equipment, far too small to notice in the course of daily life, but they are present. They are real. They are happening to you right now in this moment as you read these words. The second is not a universal constant. The second is a compromise, a convention, a local agreement among beings who share approximately the same region of space-time. When we venture beyond that region, when we launch satellites into orbit, when we send probes to distant planets, when we detect particles from distant astrophysical sources, we must remember that the seconds we count on Earth are not the seconds that passed elsewhere. The muon's second, the black hole's second, the cesium atom's second, and your second are all different. They are connected by mathematics, related by the geometry of space-time, but they are not identical. This is the reality behind the familiar word. This is what it means to say that time is relative. Not relative in the casual sense of it depends on your perspective, but relative in the technical, physical, experimentally verified sense that different observers in different states of motion or different gravitational environments genuinely experience the passage of time at different rates. The second you are living through right now is your second, defined by your position and velocity, measured by the atoms in your body vibrating at their characteristic frequencies, counted by the clocks you've built to track your local experience of duration. It is not the universe's second. The universe does not have a second. It has only the local seconds of particular observers, woven together by the mathematics of relativity into a coherent but frame-dependent structure. And so we return to the cesium atom, still faithfully emitting its 9,992, 631,970 cycles per proper second, still serving as humanity's standard of duration, still providing the reference against which all other temporal measurements are calibrated. The atom does not know that it is defining a second. The atom simply does what quantum mechanics compels it to do. The energy gap between two hyperfine levels of the cesium-133 ground state corresponds to a photon of a particular frequency, and the atom emits or absorbs such photons according to the probabilities dictated by the Schrödinger equation. We have merely attached the label second to a certain number of these cycles, a label that means something only in the context of our local measurements, our local clocks, our local experience of time's passage. Elsewhere in the universe, beings with different origins might have attached different labels to different phenomena. They might define their time units in terms of pulsars or orbital periods or the decay of exotic isotopes. They might experience durations that seem to us preposterously long or absurdly short, depending on their gravitational environment and typical velocities. They might look at our definition of the second and find it parochial, limited, bound to the specific circumstances of a rocky planet orbiting a yellow dwarf star in an unremarkable spiral galaxy, and they would be right. Our second is parochial, it is local, it is ours. But parochialism is not a failure, it is a necessity. We measure what we can measure, in the terms available to us, using the standards that make sense in our environment. The second is not diminished by being local. It is simply understood more deeply. The fleeting instant you experience when you blink, the duration you estimate when you count one Mississippi, the objective interval measured by your cesium clock. These are all manifestations of your local time, your proper time, the time that belongs to your particular journey through space-time. And yet, to understand fully what makes your second truly yours, we must confront the apparent paradoxes that arise when different seconds collide. We must examine what happens when observers moving at different velocities or residing in different gravitational environments attempt to compare their experiences of duration. We must grapple with the strange consequences that follow from the simple premise that the speed of light remains constant for all observers. For it is in these consequences that the true nature of the second reveals itself, not as a fixed quantity stamped onto the universe, but as a flexible, observer-dependent measure that stretches and compresses according to the geometry of space-time itself. Consider two clocks, identical in every way. Both are cesium-133 atomic clocks of the highest precision, constructed with the same materials, calibrated against the same standards, verified against each other until their outputs are indistinguishable. You keep one clock stationary in your laboratory. You place the other aboard an aircraft and send it around the world. When the travelling clock returns, you compare the two. What you find is not a discrepancy caused by mechanical imperfection or measurement error. What you find is that the travelling clock has accumulated fewer seconds than the stationary clock. The difference is tiny, nanoseconds over a journey of many hours, but it is real, it is measurable, and it is exactly what Einstein's equations predict. The clock that moved through space at higher velocity experienced fewer proper seconds than the clock that remained relatively stationary. Both clocks functioned perfectly. Both clocks counted their own seconds with absolute precision, but the seconds themselves were different, because the clocks traced different paths through space-time. This experiment was actually performed. In October of 1971, physicists Joseph Haffel and Richard Keating placed cesium atomic clocks aboard commercial airliners and flew them around the world, once eastward, once westward. When they compared the flying clocks to reference clocks at the United States Naval Observatory in Washington, D.C., they found discrepancies of hundreds of nanoseconds. The eastward flying clocks, which moved with the Earth's rotation and therefore travelled faster relative to the observatory's inertial frame, lost approximately 59 nanoseconds compared to the ground clocks. The westward flying clocks, which moved against the Earth's rotation and therefore travelled slower relative to that same frame, gained approximately 273 nanoseconds. These results included contributions from both special relativistic time dilation, caused by the aircraft's velocity, and general relativistic time dilation, caused by the aircraft's higher altitude and therefore weaker gravitational field. The predictions matched the observations within experimental uncertainty. The second aboard the airplane was genuinely different from the second on the ground. But this was merely a preview. The true scale of temporal discrepancy becomes apparent only when we consider velocities far greater than any airplane can achieve, or gravitational fields far stronger than Earth's modest pull. The equations of special relativity predict that time dilation becomes increasingly pronounced as velocity approaches the speed of light. At ordinary speeds, the speeds of cars, airplanes, even spacecraft, the effect is present but minuscule. At speeds approaching a significant fraction of light speed, the effect becomes dramatic. At 90% of light speed, a moving clock runs at roughly 44% the rate of a stationary clock. At 99% of light speed, it runs at roughly 14%. At 99.99% of light speed, it runs at roughly 1.4%. The closer you approach the universal speed limit, the more severely your seconds stretch relative to those of a stationary observer. This is not a technical curiosity. This is the mechanism by which the muon survives its journey from the upper atmosphere to the Earth's surface. The muon is created travelling at approximately 99.94% of light speed. At this velocity, time dilation slows the muon's internal clock by a factor of roughly 29 relative to a stationary observer on Earth. What the earthbound physicist measures as 2 microseconds of flight time corresponds to less than 70 nanoseconds of proper time for the muon itself. The muon does not experience an unusually long life. The muon experiences a perfectly ordinary life of 2.2 microseconds in its own reference frame. But that 2.2 microseconds of muon time maps onto roughly 64 microseconds of Earth time, more than enough for the particle to traverse the full thickness of the atmosphere. From the muon's perspective, something entirely different happens. The muon sees the atmosphere rushing toward it at 99.94% of light speed. At this velocity, length contraction, the spatial counterpart of time dilation, compresses the atmosphere to a fraction of its rest frame thickness. What we measure as 15 kilometers becomes, in the Muon's reference frame, roughly 520 meters. The Muon crosses this contracted distance in perfectly ordinary time, dying after its expected 2.2 microseconds. But during that brief interval, the Earth's surface has rushed up to meet it. Both perspectives are equally valid. Both are equally real. The mathematics of special relativity ensures that they agree on the physically observable outcome. The muon reaches the surface. They differ only in their accounting of where the extra time or contracted distance came from. This symmetry lies at the heart of relativity's conceptual challenge. There is no absolute answer to the question, how long did the muon live? There is only the proper time measured in the muon's rest frame and the dilated time measured in the Earth's rest frame, connected by a mathematical relationship that depends on relative velocity. The muon's second is not Earth's second. Earth's second is not the muon's second. Both are legitimate measurements of duration, differing because they correspond to different paths through space-time. The same principle applies with even more dramatic consequences in the vicinity of extreme gravitational fields. Near a black hole, the curvature of space-time becomes so severe that time dilation reaches factors that dwarf anything achievable through velocity alone. Consider a black hole with a mass of 10 solar masses, A modest black hole by astrophysical standards, the remnant of a collapsed massive star. The event horizon of this black hole lies at a radius of approximately 30 kilometers from the central singularity. At this boundary, the escape velocity equals the speed of light, and nothing, not matter, not energy, not information, can travel outward. But even outside the event horizon, in the region where escape is still theoretically possible, space-time is warped so severely that time runs at a crawl. At twice the event horizon radius, 60 kilometers from the centre, time runs at approximately 71% of the rate experienced by a distant observer. A clock hovering at this location would tick once for every 1.4 ticks of a clock in interstellar space. At 1.5 times the event horizon radius, 45 kilometers from the centre, time runs at approximately 58% of the distant rate. At 1.1 times the event horizon radius, just 33 kilometers from the centre, time runs at roughly 30% of the distant rate. And as you approach the event horizon itself, time dilation becomes arbitrarily extreme. At a distance of just 1 millimeter above the event horizon, time runs at roughly 0.2% of the distant rate, a factor of more than 5,000. 1 second of proper time at this location corresponds to more than an hour and a half of time in the distant universe. 1 hour of proper time corresponds to more than 7 months outside. 1 year of proper time corresponds to more than 5 millennia. These are not theoretical extrapolations beyond the reach of physical confirmation. While we cannot yet place clocks in the immediate vicinity of black holes, we can observe their effects through other means. We can watch stars orbiting the supermassive black hole at the centre of our galaxy, their orbits precisely matching the predictions of general relativity. We can detect gravitational waves from merging black holes, their waveforms encoding information about the extreme space-time curvature in their immediate vicinity. We can observe light from background sources being bent and delayed as it passes near massive objects. The delay is exactly consistent with the gravitational time dilation those objects produce. The evidence is overwhelming and consistent across multiple independent observations. Time really does run slower in stronger gravitational fields. The second really is different depending on where you are in the universe. But the most extreme example yet discovered may be the environment surrounding certain rapidly rotating black holes. When a black hole spins, it drags space-time itself around with it in a phenomenon known as frame dragging, or the lens-thirring effect. This rotation creates additional complications in the relationship between different observers' seconds. Outside a spinning black hole lies a region called the ergosphere, bounded by the outer surface of the static limit, the boundary beyond which it becomes impossible to remain stationary relative to distant stars without travelling faster than light. Within the ergosphere, every observer must rotate with the black hole, dragged along by the swirling of space-time itself. The time dilation effects in this region depend not only on distance from the event horizon, but also on the direction and speed of the observer's forced rotation. An observer falling inward experiences one version of time. An observer hovering at constant radius, rotating with the minimum required angular velocity, experiences another. An observer attempting to orbit in the opposite direction finds the attempt impossible. The geometry of space-time simply does not permit retrograde motion within the ergosphere. Near the inner edge of the ergosphere of a maximally rotating black hole, time dilation can reach factors of millions or billions relative to distant observers. An observer who somehow survived at this location, somehow resisted the tremendous tidal forces, somehow maintained a stable position against the gravitational pull, could watch the distant universe evolve at an incomprehensible rate. Civilizations could rise and fall in what seemed like moments. Stars could form, burn through their nuclear fuel, and explode as supernovae in what seemed like hours. The entire future history of the cosmos could unfold before the observer's eyes while they experienced only a single ordinary human lifetime. This scenario is not merely hypothetical. It has been explored in scientific literature as a potential mechanism for extreme time travel into the future. An astronaut who could somehow approach a rapidly rotating supermassive black hole, spend a subjective year in its immediate vicinity, and then escape back to distant space would find that millions or billions of years had passed in the outside universe. Everyone and everything they had ever known would be long gone. New generations of stars would have formed. New civilizations might have risen. The entire character of the cosmos might have changed beyond recognition. The astronaut would have travelled into the far future, not through any special propulsion technology, but simply by taking advantage of the natural time dilation that extreme gravity produces. The price of such a journey would be absolute and permanent. There is no way to return to the time you left. The seconds that passed in the outside universe, while you lingered near the black hole, cannot be recovered. Your proper time moved forward at its normal rate from your perspective, but the distant universe moved forward at its vastly accelerated rate from that same perspective. When you leave the black hole's vicinity, you find yourself in a future that has forgotten you ever existed. This asymmetry, the fact that you can travel into the future but not into the past, is not a limitation of our current technology. It is a fundamental feature of space-time geometry. The mathematics of general relativity permits closed time-like curves under certain exotic conditions, theoretical paths through space-time that loop back to their starting point in time. But these solutions require configurations of matter and energy that have never been observed and may be physically impossible. Rotating cylinders of infinite length, wormholes stabilized by negative energy density, cosmic strings moving at nearly light speed. In the space-time geometries that actually exist in our universe, time travel into the past appears to be strictly forbidden. Time travel into the future, however, is permitted, is routine, and is happening to every object in the universe at every moment. Every difference in velocity or gravitational potential between two observers produces a difference in the rate at which they experience time. The GPS satellites orbiting Earth are travelling into the future slightly faster than the ground stations that communicate with them. The crew of the International Space Station is travelling into the future slightly faster than the people on the ground below. The muons created in cosmic ray showers are travelling into the future dramatically faster than the physicists who detect them. All of these objects are exploiting, passively, unintentionally, inevitably, the time dilation effects that relativity predicts. And this brings us to a profound realization about the nature of the second itself. When we define the second as 90,192,631 oscillations of the cesium-133 atom, we were not defining a universal constant. We were defining a procedure, a set of instructions for constructing a clock that measures proper time along its own world line through space-time. Every cesium clock measures proper time. Every cesium clock ticks at exactly the same rate when measured against other clocks that share its reference frame. But cesium clocks in different reference frames, moving at different velocities, residing at different gravitational potentials, will disagree with each other when compared. This is not a flaw in the definition. This is a feature of the universe. The definition of the second is correct. It simply applies differently in different contexts. The implications of this realization cascade outward into every domain of physics. Consider the concept of simultaneity, the intuitive notion that two events can be said to happen at the same time. In everyday experience, simultaneity seems obvious and unambiguous. When a starting gun fires and two sprinters begin running at the same moment, we have no trouble identifying that moment as simultaneous. But relativity reveals that simultaneity is just as observer-dependent as the duration of a second. Two events that are simultaneous in one reference frame are not simultaneous in another reference frame moving relative to the first. There is no absolute fact of the matter about whether two distant events happened at the same time. There is only the relative judgment of particular observers, each of whom is entitled to their own internally consistent accounting of temporal relationships. This is not an abstraction. Consider two locations on opposite sides of the Earth, say London and Sydney, separated by roughly 17,000 kilometres. According to a clock at rest relative to Earth, events at these two locations can be simultaneous in the ordinary sense. But according to an observer passing Earth at high velocity, say a cosmic ray proton travelling at 99.9% of light speed, the same two events might be separated by significant intervals of time, with London's event occurring noticeably before or after Sydney's event, depending on the direction of the observer's motion. For a proton travelling from London towards Sydney, events in Sydney lie in the proton's future direction, and time dilation effects cause Sydney events to appear to occur later than simultaneous London events would. For a proton travelling in the opposite direction, the ordering reverses. Neither perspective is wrong. Both are valid descriptions of the same physical reality from different reference frames. The universe does not provide a cosmic clock that marks absolute time for all observers. The universe does not distinguish between past and future in the way our local experience suggests. What the universe provides instead is a geometric structure, the metric of space-time, that relates different observers' experiences to each other through precise mathematical relationships. Each observer has their own proper time, their own seconds, their own experience of duration. These proper times are woven together by the geometry of space-time into a coherent whole, but that whole does not privilege any single observer's perspective as the true one. This is what it means to say that time is a dimension. In ordinary speech, we think of time as something fundamentally different from space, the container in which events occur, the river that carries us from past to future, the mysterious medium through which change happens. But relativity reveals that time is more properly understood as a fourth dimension of a unified four-dimensional space-time, differing from the three spatial dimensions only in the sign of its contribution to the space-time interval. The mathematics of special relativity treats time and space as interchangeable components of a single geometric structure. A rotation in ordinary three-dimensional space mixes the x, y, and z coordinates of objects without changing their distances from the origin. A rotation in four-dimensional space-time, what we call a Lorentz transformation, mixes the time and space coordinates of events without changing their space-time intervals from the origin. Velocity through space corresponds to a rotation of your time axis relative to the time axis of other observers. The faster you move, the more your time axis is rotated, and the more your seconds diverge from the seconds of stationary observers. Picture this concretely. Imagine a two-dimensional diagram with one axis representing space, say the x direction, and the other axis representing time. Your world line through space-time is a path in this diagram, showing your position at each moment. If you are stationary, your world line points straight up, parallel to the time axis. If you are moving, your world line is tilted, pointing partly along the space axis as well as the time axis. The angle of this tilt corresponds to your velocity. As you approach the speed of light, your world line approaches a 45-degree angle, corresponding to the trajectory of a light ray. But here is the key insight. Your proper time, the time measured by your own clock, the time you experience passing in your own frame of reference, is not the vertical projection of your world line onto the time axis. Your proper time is the length of your world line itself, measured using the space-time metric. And because the space-time metric has a different sign for the time coordinate than for the space coordinates, a tilted world line is actually shorter than a vertical world line connecting the same two-time coordinates. This is why moving clocks run slow. They are taking a shorter path through space-time, and proper time measures path length. This geometric perspective transforms our understanding of time dilation from a strange phenomenon into a natural consequence of space-time geometry. When the muon travels from the upper atmosphere to the Earth's surface at nearly light speed, it is taking a shortcut through space-time. Its world line is severely tilted relative to the world lines of stationary observers, and as a result, less proper time accumulates along its path. The muon is not somehow cheating death or experiencing magic. The muon is simply following the rules of space-time geometry, which dictate that rapidly moving objects accumulate less proper time than slowly moving ones. The muon's 2.2 microsecond lifetime is exactly correct. It merely corresponds to a much longer interval of coordinate time as measured by earthbound observers. The same geometric perspective illuminates gravitational time dilation. In general relativity, gravity is not a force pulling objects toward massive bodies. Gravity is the curvature of space-time caused by the presence of mass and energy. Objects in free fall follow geodesics, the straightest possible paths through curved space-time, and what we interpret as gravitational attraction is simply the convergence of geodesics toward regions of high space-time curvature. Near a massive object, space-time is curved in such a way that proper time accumulates more slowly along paths that remain close to the mass. A clock at the bottom of a gravity well traces a world line through more severely curved space-time than a clock at the top, and as a result, less proper time accumulates along the lower clock's path. This is not a slowing of some universal time. This is a geometric fact about the length of world lines through curved space-time. The mathematics of this curvature is expressed in Einstein's field equations, which relate the distribution of mass and energy in a region of space-time to the curvature of that space-time. These equations are notoriously complex. They constitute a system of 10 coupled non-linear partial differential equations that can be solved exactly only in cases of high symmetry, but the principle they express is conceptually simple. Matter tells space-time how to curve, and space-time tells matter how to move. The curvature that matter produces affects the geometry along which all objects travel, including the geometry that determines the relationship between different observers' proper times. A clock near a massive object moves through a different space-time geometry than a clock far from that object, and the difference in geometry produces a difference in the seconds those clocks measure. This is why GPS satellites must account for relativistic effects. The satellites orbit at an altitude of approximately 2,200 kilometers, where the gravitational field is weaker than at Earth's surface. According to general relativity, their clocks should run faster than ground-based clocks by about 45 microseconds per day due to reduced gravitational time dilation. But the satellites are also moving at approximately 14,000 kilometers per hour relative to the ground, and according to special relativity, their clocks should run slower by about 7 microseconds per day due to velocity-based time dilation. The net effect is that satellite clocks run faster by about 38 microseconds per day. If uncorrected, this discrepancy would cause GPS position errors to accumulate at a rate of roughly 10 kilometers per day. The entire system would become useless within minutes. The fact that GPS works at all is a continuous, practical, everyday verification that both special and general relativistic time dilation are real and must be accounted for in precision timekeeping. You carry this verification in your pocket. Every time you use a map application to navigate, every time you check your location on a GPS-enabled device, you're relying on corrections derived from Einstein's equations. The satellites are experiencing different seconds than you are, and unless that difference is compensated, the timing signals they send will not synchronize correctly with your ground-based position. The second on the satellite and the second on the ground are connected by mathematics, but they are not the same second. They are different experiences of duration, arising from different paths through space-time. And here, perhaps, is the deepest insight that emerges from this examination of time's relativity. The second is not something the universe provides. The second is something observers create. Each observer, travelling along their unique world line through space-time, experiences the passage of proper time at exactly 1 second per second. By definition, because proper time is defined as the time measured by a clock moving with the observer. But the coordination of different observers' seconds, the comparison of their experiences, the conversion of one frame's measurements into another frame's measurements, these are mathematical operations performed using the geometry of space-time, not appeals to some absolute temporal standard that stands outside the relativistic framework. The universe has no heartbeat. The universe keeps no master time. What the universe has is a geometric structure that relates different observers to each other, allows them to communicate and compare measurements, and ensures that their different perspectives are consistent with each other, even when they differ dramatically in their accounting of duration. Your second, the muon second, the black hole's second, and the cesium atom's second are all legitimate measures of proper time along different world lines. They differ because the world lines differ. They agree when properly transformed because the mathematics of relativity provides a consistent framework for relating them. This framework is not arbitrary. It is dictated by the fundamental symmetries of nature, the requirement that the laws of physics must take the same form for all inertial observers, the requirement that the speed of light must be the same in all reference frames. These symmetries constrain the structure of space-time geometry uniquely. There is only one way to build a universe that respects these symmetries, and that is the universe we inhabit, a universe where time dilates with velocity, where time slows in gravitational fields, where simultaneity is relative, and where the second is a local measure rather than a cosmic constant. The cesium atom, faithfully emitting its 9,992,631,070 oscillations per proper second, does not know any of this. The atom simply responds to the quantum mechanical laws that govern its behaviour, transitioning between energy levels according to probabilities that have remained constant since the first cesium atoms formed in ancient stellar explosions. But we know it now. We understand that the second we have defined is our second, bound to our location in space-time, valid for our measurements and our clocks, but not privileged above the seconds of other observers in other circumstances. We understand that the muon's fleeting existence and the black hole's eternal patience are not contradictions but consequences of the same underlying geometry. We understand that time, far from being the simple backdrop against which events occur, is itself a dynamic participant in the physics of the universe, shaped by matter, warped by motion, and experienced differently by every observer who moves through it. And with this understanding, we begin to see the true scope of the question that opened this exploration. 1 second is not one thing. 1 second is many things, depending on who measures it, where they measure it, and how they are moving when they do so. The word second is a label we attach to our local experience of duration, a label that travels with us through space-time but does not describe the same interval everywhere. Somewhere in the universe, a muon is being created this instant, destined to live for exactly 2.2 microseconds of its own proper time, which will correspond to dozens of microseconds in the laboratory that observes it. Somewhere else, matter is spiralling into a black hole, its final moments stretched into centuries by the extreme time dilation near the event horizon. Somewhere else still, a cesium atom is ticking away in perfect isolation, defining a second that applies only to its immediate vicinity, a second that would differ from the second defined by an identical atom in a different gravitational field or a different state of motion. All of these seconds are real, all of them are correct, and all of them are happening right now. Though even that phrase, right now, is suspect, because simultaneity itself depends on the observer's reference frame. The implications of this realization extend far beyond the theoretical. They reach into the practical machinery of civilization, into the systems we depend upon daily, without ever considering the temporal complexities that lurk beneath their operation. Consider the satellites that orbit above your head at this very moment, the constellation of global positioning system spacecraft that allow your phone to determine your location within a few meters. These satellites are not merely broadcasting signals, they are engaged in an ongoing negotiation with the fabric of space-time itself, a negotiation that would cause the entire system to fail catastrophically within hours if we ignored the lessons of relativity. A GPS satellite orbits at an altitude of approximately 20,200 kilometers above Earth's surface, travelling at roughly 14,000 kilometers per hour. At this velocity, special relativity predicts that the satellite's clocks will run slower than identical clocks on the ground by about 7 microseconds per day. This is the familiar time dilation of motion, the same effect that grants the muon its extended laboratory lifetime. If this were the only relativistic effect in play, your GPS receiver would gradually accumulate positioning errors as the satellite clocks drifted out of synchronization with ground-based standards. But there is another effect, working in the opposite direction. At 20,200 kilometers altitude, the satellite experiences a weaker gravitational field than clocks on Earth's surface. General relativity predicts that clocks in weaker gravitational fields run faster than clocks in stronger fields. This gravitational time dilation causes the satellite clocks to gain approximately 45 microseconds per day relative to ground clocks. The net effect is a gain of about 38 microseconds per day. This sounds trivially small. 38 microseconds is less time than it takes for light to travel 7 miles. But GPS signals travel at the speed of light, and the system determines position by measuring the precise timing of signals from multiple satellites. A timing error of 38 microseconds corresponds to a positioning error of more than 11 kilometers. If GPS engineers ignored relativity, your navigation system would place you in the wrong city within a single day. Within a week, the errors would accumulate to hundreds of kilometers. The system would become not merely inaccurate, but useless. The solution requires deliberately missetting the satellite clocks before launch. The atomic clocks aboard GPS satellites are tuned to oscillate at a slightly different frequency than identical clocks on the ground, pre-compensating for the relativistic effects they will experience in orbit. This is not a minor adjustment or an approximate correction. The engineers calculate the precise amount of frequency offset required by the combined effects of special and general relativity, then program the clocks accordingly. Every time you use GPS to navigate to an unfamiliar address, you are relying on calculations that Einstein first performed more than a century ago. Calculations that recognize the second aboard a satellite is not identical to the second on the ground. This is relativity made practical, made essential, made invisible. The average person using GPS navigation has no awareness that their technology depends on the non-universality of time. They simply trust the system to work, unaware that it works precisely because engineers understood that 1 second is not the same everywhere. that the satellites inhabit a different temporal environment than the receivers on Earth's surface, and that failing to account for this difference would render the entire system worthless. But GPS represents only the beginning of our practical entanglement with relativistic time. As technology advances, as our measurements become more precise, we find ourselves confronting the heterogeneity of time at increasingly intimate scales. The optical atomic clocks now being developed in laboratories around the world can detect gravitational time dilation over vertical distances of mere centimetres. Raise one of these clocks by the height of a single stair step, and its tick rate measurably increases relative to an identical clock at floor level. The difference is unimaginably small, roughly 1 part in 10 to the 18th power for each metre of altitude. But it is real, and it is detectable. This sensitivity transforms the clock from a mere timekeeper into a probe of gravitational fields, a sensor capable of mapping variations in Earth's gravitational potential with extraordinary precision. Geophysicists envision using networks of optical clocks to monitor changes in the planet's mass distribution, detecting the movement of underground water, the settling of fault lines, the flow of magma beneath volcanic regions. The same non-universality of time that complicates our philosophical understanding of duration becomes a practical tool for understanding our planet. And as our measurements become more precise, the boundaries between timekeeping and fundamental physics increasingly blur. The current definition of the second, based on cesium-133 transitions, achieves an accuracy of roughly 1 part in 10 to the 16th power. This means a cesium clock would neither gain nor lose a full second over approximately 300 million years of continuous operation. But optical clocks have already demonstrated performance exceeding this by factors of 100 or more. They achieve accuracies of 1 part in 10 to the 18th power, meaning they would require the entire age of the universe to accumulate a 1-second error. At this level of precision, entirely new phenomena become observable. The clocks become sensitive to fluctuations in fundamental constants, to the passage of dark matter through the laboratory, to the gravitational waves rippling through space-time from collisions of distant black holes. The second, that humble unit we inherited from ancient astronomical observations, becomes a window into the deepest structure of reality, and every improvement in our ability to measure the second more precisely reveals more clearly how fragmented the concept truly is across different locations and conditions. Consider what happens when we attempt to establish a unified timescale for Earth, a single standard that coordinates the clocks of different nations and laboratories. This is the mission of International Atomic Time, maintained by the International Bureau of Weights and Measures in Paris. The Bureau collects data from several hundred atomic clocks, distributed across dozens of laboratories worldwide, combining their measurements through sophisticated statistical algorithms to generate a weighted average that represents humanity's best approximation of a stable, uniform timescale. But here is the difficulty. These clocks are not at the same altitude. A clock in Boulder, Colorado operates at an elevation of 1,650 meters above sea level. A clock in Braunschweig, Germany, sits at roughly 80 meters elevation. A clock in Tokyo is nearly at sea level. By the dictates of general relativity, these clocks tick at measurably different rates. The Boulder clock runs faster than the Tokyo clock by several parts in 10 to the 16th, a difference easily detected by modern standards. To combine these measurements into a single coherent timescale, the Bureau must correct each clock's readings for its gravitational environment, translating all measurements to a hypothetical reference surface called the GOE. The geoid represents the shape Earth's oceans would take if they covered the entire planet and remained undisturbed by tides, currents, or weather, a surface of constant gravitational potential. By correcting all clocks to this common reference, the Bureau creates a timescale that is as close to universal as possible, given the constraints of relativity. But even this corrected timescale applies only to observers at rest on the geoid. An observer moving relative to Earth's surface, or an observer at a different gravitational potential, would disagree with this timescale according to the standard relativistic transformations. International Atomic Time is not a cosmic standard. It is a carefully constructed terrestrial standard, valid for the purposes of human civilization, but not extending its authority beyond the tiny gravitational well of our particular planet. This limitation becomes acute when we consider the challenges of interplanetary navigation. When NASA communicates with spacecraft exploring the outer solar system, signals travel for hours across billions of kilometers of vacuum. The timing precision required to navigate these missions demands that controllers account for the relativistic effects experienced by the spacecraft. A probe approaching Jupiter exists in a different gravitational environment than Earth, orbiting a massive planet whose gravitational field warps time in its vicinity. The spacecraft's clocks run at rates that differ from Earth clocks by amounts that, while small, accumulate over the months and years of a mission. For missions to Mars, these corrections are modest, but real. For missions to the outer planets, they become more significant. For any future mission to the vicinity of a neutron star or black hole, admittedly beyond current technology but not beyond imagination, the corrections would dominate all other considerations. The spacecraft's seconds would stretch so dramatically relative to Earth's that meaningful real-time communication would become impossible. Mission controllers would send a command and wait, not merely for the light travel time, but knowing that the spacecraft's clocks were running at fundamentally different rates, that the very concept of simultaneity between Earth and the spacecraft had become ambiguous. The universe does not permit us to maintain a single synchronized clock network that spans different gravitational environments and different states of motion. The physics forbids it. We can establish local time standards, we can create conventions for translating between them, we can build theoretical frameworks that relate different observers' measurements to each other, but we cannot identify one particular tick rate as the true rate of time and dismiss all others as distorted reflections. Every observer's proper time is equally valid. Every observer's second is equally real. This insight forces a profound reconceptualization of what time actually is. For centuries, physicists and philosophers debated whether time was absolute or relative, whether it flowed independently of the events it measured, or whether it was somehow constructed from the relationships between events. Newton famously sided with absolute time, declaring that absolute true and mathematical time of itself and from its own nature flows equably without relation to anything external. This Newtonian vision dominated physics for 200 years. It formed the backdrop against which mechanics, thermodynamics, and electromagnetism were developed. It seemed so intuitively correct, so aligned with everyday experience, that questioning it appeared almost absurd. Then came Einstein, and the Newtonian vision collapsed. Not because it was useless. Newtonian physics remains extraordinarily accurate for everyday circumstances, but because it was fundamentally incomplete. At high velocities, in strong gravitational fields, in the extreme environments where the universe reveals its true nature, Newton's absolute time simply does not exist. What exists instead is the geometric structure of space-time, a four-dimensional manifold in which time and space are woven together into a unified whole, and in which different observers carve out different temporal axes depending on their motion and their gravitational environment. The implications extend to the most fundamental questions about the nature of reality. If time does not flow at a single universal rate, what does this imply about the apparent passage of events from future to present to past? If different observers disagree about which events are simultaneous, can we even speak coherently about the present moment as a global phenomenon? These questions have occupied philosophers and physicists for over a century, and they remain controversial. One perspective, often called the block universe view, holds that past, present, and future all exist equally in the four-dimensional space-time structure. From this viewpoint, the apparent flow of time is something like an illusion, a feature of consciousness rather than a feature of fundamental physics. Just as all points of space exist simultaneously, even though we occupy only one location, all moments of time exist equally even though we experience them one at a time. The universe is not a three-dimensional stage on which temporal drama unfolds. It is a four-dimensional sculpture, complete and eternal, which we experience in slices as our world lines thread through it. This view is not universally accepted. Many physicists and philosophers resist the apparent elimination of becoming, of genuine temporal passage, that the block universe seems to imply. They argue that while relativity certainly demonstrates the frame dependence of simultaneity, it does not necessarily eliminate the reality of temporal flow along each observer's world line. The debate continues, deeply technical, philosophically charged, and unresolved. What is not in dispute is that the second you experience, the second ticking away on your wristwatch at this moment, is not a slice of some universal temporal structure. It is your slice, bound to your motion, shaped by your gravitational environment, as personal as your position in space. When you claim that 1 second has passed, you're making a claim about your world line through space-time, not about the universe as a whole. Other observers on other world lines would pass that same interval differently, and their passing would be equally correct. This personalization of time has consequences that seem almost mystical until we recognize them as straightforward physics. Consider the phenomenon of gravitational redshift, first predicted by Einstein and first confirmed in 1959 by the Pound-Repke experiment. When light climbs out of a gravitational well, it loses energy. This energy loss manifests as a decrease in the light's frequency, a shift toward the red end of the spectrum. The light from stars, for instance, is slightly red-shifted by the time it reaches Earth, its wavelength stretched by the effort of escaping the star's gravitational field. But frequency is just the inverse of period, and period is just time. When we say that light has been redshifted, we are saying that the time between wave crests has increased. The light is telling us, through the stretching of its waves, that time runs differently at the source than at the destination. Every photon that travels between gravitationally distinct locations carries encoded in its frequency information about the relative rates of time at its point of emission and its point of absorption. The universe is saturated with these temporal messages, photons streaming from stars to planets to galaxies, each one a tiny telegram reporting on the local tick rate at its origin. This gravitational redshift affects not only light but all periodic processes. Atoms vibrate at frequencies determined by quantum mechanics, and these frequencies serve as the basis for our atomic clocks. But an atom in a strong gravitational field vibrates at a frequency that appears lower to an observer in a weak gravitational field. The atom is not malfunctioning. The atom is reporting accurately on its local experience of time. The discrepancy arises because different locations have different local times, and comparing them reveals their inequality. The most extreme examples of this temporal inequality occur near black holes, those enigmatic objects where gravity becomes so intense that even light cannot escape. The event horizon of a black hole marks a point of no return, a boundary beyond which all world lines lead inward and none lead out. But it also marks a boundary of temporal extremity. As an object approaches the event horizon, its clocks, as observed from outside, slow asymptotically toward zero. An external observer watching a spacecraft fall into a black hole would see the spacecraft's motion slow to a crawl, its clock ticking ever more sluggishly, its final approach to the horizon stretched across infinite external time. From the external perspective, the spacecraft never quite crosses the event horizon. It freezes there, its image reddening and dimming as the light it emits loses energy climbing out of the increasingly severe gravitational well. Yet from the spacecraft's own perspective, from the perspective of clocks aboard the vessel, nothing unusual happens at the horizon. The spacecraft crosses in finite proper time, experiencing no anomaly at the threshold, and continues inward toward whatever fate awaits at the singularity. The passengers might experience mere seconds between crossing the horizon and reaching their end. Those seconds would correspond to vast spans of external time. The entire future history of the external universe might unfold while the spacecraft makes its brief interior journey. Which experience is correct? Both are. The external observer is not wrong to say that the spacecraft takes infinite time to cross the horizon. The spacecraft's passengers are not wrong to say that they cross in mere seconds. They are simply measuring different quantities, external coordinate time versus proper time along the spacecraft's world line, and these quantities differ because the geometry of space-time differs along the two world lines. The black hole represents the ultimate expression of temporal fragmentation. A single event, the crossing of the horizon, can be assigned a finite proper time or an infinite coordinate time depending on which observer is doing the timing. The second is not merely stretched or compressed here. The very meaning of temporal measurement becomes ambiguous, dependent on choices about how to slice space-time that have no privileged answer. And this ambiguity, so extreme near black holes, exists in diluted form everywhere in the universe. Every gravitational gradient, every relative motion, introduces some degree of temporal disagreement between observers. The disagreements are usually tiny, often undetectable by any practical means, but they are always present. The fabric of space-time is stitched with them, a patchwork of local proper times that can be related to each other mathematically, but cannot be reduced to a single universal clock. We began this exploration with the cesium atom, faithfully emitting its 9 billion oscillations with each passing proper second. We have travelled far from that atom, through the extended lifetimes of relativistic muons, past the warped space-time of orbiting satellites, into the extreme gravitational environment surrounding black holes. And at every step we have found the same lesson repeated in different guises. The second is local, the second is personal. The second is a measure of the interval along one particular path through space-time, rather than a universal metronome beating the same rhythm everywhere. The cesium atom does not know this. The atom simply oscillates according to the quantum mechanical rules that govern its behaviour, indifferent to the philosophical implications of its precision. But we know it now. We understand that our definition of the second, elegant and practical as it is, applies only to our immediate vicinity, only to clocks that share our gravitational environment and our state of motion. The question that remains, then, is not whether the second is universal. We have established beyond doubt that it is not. The question is what we do with this knowledge. How does civilization function when its fundamental unit of time is revealed to be local rather than absolute? How do we coordinate activities across a planet where every location experiences time at a subtly different rate? And what happens when our ambitions extend beyond this planet, when we reach for the Moon and Mars and eventually the stars themselves? The answer begins with an acknowledgement that we already live in this fractured temporal reality. We simply pretend otherwise because the pretense works well enough for most purposes. The difference in clock rate between someone standing at sea level and someone atop Mount Everest is approximately 30 microseconds per year, 30 millionths of a second across 12 months of continuous timekeeping. For scheduling meetings, catching flights, celebrating birthdays, this difference is utterly negligible. No human activity requires synchronization at the microsecond level over annual timescales. We can treat Earth's surface as if it were a single temporal domain without practical consequence. But practical consequence is not the same as physical reality. The difference is there, accumulating quietly, whether we choose to acknowledge it or not. And as our technology grows more precise, as our measurements grow more sensitive, we find ourselves forced to reckon with discrepancies that earlier generations could safely ignore. Consider the challenge of defining a universal time standard for Earth itself. The International Bureau of Weights and Measures in Paris maintains something called International Atomic Time, or TAI, which represents the weighted average of roughly 450 atomic clocks distributed across laboratories in more than 80 countries. These clocks do not tick at exactly the same rate. They cannot, because they sit at different altitudes, experience different gravitational potentials, and move at different velocities as Earth rotates beneath them. The clocks in Boulder, Colorado, tick faster than the clocks in Greenwich, England, by approximately 15 microseconds per year, owing primarily to Boulder's higher elevation. The clocks in Tokyo tick at yet another rate, the clocks in Sydney at another still. To combine these readings into a single time standard, the International Bureau must apply relativistic corrections. Each contributing clock is mathematically transported to a reference surface, specifically the geoid, an imaginary surface of constant gravitational potential that approximates mean sea level. The clock readings are adjusted to reflect what they would have recorded had they been located on this reference surface, rather than at their actual positions. Only after these corrections are applied can the readings be meaningfully averaged. International Atomic Time is not the time kept by any actual clock. It is a mathematical construction, a theoretical time that would be kept by an idealized clock on an idealized surface. The second we use for international coordination is not a measured quantity, but a calculated one, derived from hundreds of imperfect measurements, corrected for relativistic effects, and averaged according to complex weighting schemes. This system works remarkably well. International Atomic Time maintains stability at the level of a few parts in 10 to the 16th, equivalent to an uncertainty of roughly 1 second in 300 million years. For terrestrial purposes, this precision far exceeds any conceivable requirement. We have in effect created a fictional universal time for Earth by agreeing to pretend that all clocks sit on the same gravitational surface and by applying the corrections necessary to maintain this fiction. But extend our ambitions beyond Earth, and the fiction becomes harder to sustain. Consider the Moon, which orbits at an average distance of approximately 384,000 kilometers from Earth's center. The gravitational potential at the lunar surface differs substantially from the potential at Earth's surface. A clock on the Moon would tick faster than a clock on Earth by approximately 56 microseconds per day, not per year, per day. Over the course of a month, the discrepancy accumulates to nearly 2 milliseconds. Over a year, to roughly 20 milliseconds. 20 milliseconds might still sound insignificant, but consider its implications for precision navigation. Light travels approximately 6,000 kilometers in 20 milliseconds. A positioning error of 6,000 kilometers would place you in the wrong hemisphere. For any activity requiring precise coordination between Earth and Moon, robotic operations, communication synchronization, eventual human habitation, this temporal drift cannot be ignored. The Moon requires its own time standard, its own definition of the second calibrated to its own gravitational environment. NASA and the European Space Agency have begun serious discussions about establishing a lunar time standard, a reference time specifically for the Moon and its vicinity. This standard would not be synchronized to International Atomic Time in any simple sense. It would tick at its own rate, faster than terrestrial time, accumulating a growing offset as the years pass. Coordinating activities between Earth and Moon would require constant translation between two temporal frameworks that drift apart at a rate of 56 microseconds daily. Mars presents an even more dramatic challenge. The average distance to Mars varies between approximately 55 million and 400 million kilometers, depending on orbital position. Light takes between 3 and 22 minutes to travel between the planets. This communication delay alone disrupts any notion of simultaneity between Earth and Mars. When you receive a message from Mars, you are learning about events that occurred somewhere between 3 and 22 minutes ago. When your response arrives on Mars, the Martian present will have advanced by another 3 to 22 minutes. There is no shared now between the two worlds, only an exchange of information about each other's past. Beyond the communication delay, Mars experiences its own gravitational environment. The Martian surface sits at a gravitational potential different from Earth's surface, and clocks there tick at a different rate. The difference is smaller than for the Moon, approximately 2 to 3 microseconds per day, because while Mars has less mass than Earth, a clock on Mars also sits farther from the Sun's gravitational influence than a clock on Earth does. The two effects partially offset each other, though not completely. More importantly, Mars has its own rotation rate, its own definition of a day. The Martian solar day, called a sol, lasts approximately 24 hours and 37 minutes by Earth reckoning. Mission controllers working with Mars rovers have experimented with living on Mars time, shifting their sleep schedules by 37 minutes each day to stay synchronized with the rover's operational cycle. They found the experience disorienting, their bodies fighting against a diurnal rhythm incompatible with Earth's day-night cycle. Eventually, most missions abandon Mars time for Earth time, accepting the operational complications this choice created. A permanent human settlement on Mars would face this choice in a more acute form. Would Martians live on Earth time, maintaining coordination with the home world at the cost of perpetual circadian confusion? Would they adopt Mars time, accepting the growing divergence from Earth's temporal framework? Would they create an entirely new calendar, with Martian months and Martian years measured in sols rather than seconds? These are not merely administrative questions. They touch on fundamental issues of identity and belonging. What does it mean to share time with someone? What does it mean to lose that shared time? The further we travel from Earth, the more severe these questions become. Jupiter's gravitational field creates time dilation effects roughly 10 times greater than Earth's. A clock in Jupiter's upper atmosphere would tick slower than a clock on Earth by approximately 600 microseconds per day due to the intense gravity. Saturn, Uranus, Neptune. Each creates its own temporal environment, its own definition of how quickly time passes. The outer solar system is not merely cold and dark, it is temporally foreign, running on clocks that tick at rhythms incompatible with anything we experience on Earth. And yet all of this pales beside the temporal alienation that would accompany true interstellar travel. We established in earlier portions of this exploration that reaching the stars within a human lifetime requires velocity substantial enough to produce significant time dilation. A spacecraft travelling at 90% of the speed of light would experience time at less than half the rate of the civilization it left behind. The travellers would age 10 years while their homeworld aged 23. At 99% of light speed, the ratio becomes 7 to 1. At 99.9%, 22 to 1. These ratios represent more than just clock discrepancies. They represent the fragmentation of human society across incompatible temporal frames. Imagine a generation ship departing Earth for a star system 10 light-years distant. The ship accelerates to 99% of light speed, maintaining this velocity for most of the journey. The crew experiences perhaps 3 years of ship time crossing the interstellar void. They arrive at their destination, establish communication with Earth, and report their success. But their message takes 10 years to reach Earth. By the time anyone hears from them, 13 Earth years have passed since their departure. The crew has aged 3 years. Their families have aged 13. Children born after the ship departed have become teenagers. Parents who were middle-aged at the farewell have become elderly. The temporal gulf between the travellers and those they left behind has widened into an unbridgeable chasm. Should the travellers return home, the chasm would widen further still. Another 3 years of ship time, another 13 years of Earth time. The round trip that felt like 6 years to the crew has consumed 26 years for everyone they knew. The travellers return to a world that has moved on without them, a world where their contemporaries are a generation older, where their cultural references are obsolete, where the society they remember exists only in historical archives. They have not merely travelled through space, they have travelled through time in a way that cannot be reversed. This is the price of relativistic travel, paid in temporal isolation. The faster you go, the more you become a stranger to your own era. The cosmos does not merely impose spatial distances between the stars, it imposes temporal distances as well, forcing travellers to choose between brief journeys that span generations or generational journeys that span centuries. There is no speed at which the distance can be crossed without this cost. There is no technology that can eliminate the temporal penalty. It is woven into the fabric of reality itself. Consider what this means for any attempt at interstellar civilization. A network of human colonies scattered across multiple star systems would not share a common present. Messages sent from one world would arrive decades or centuries later at another. A colony at Alpha Centauri, 4 light-years distant, would receive news from Earth that was already 4 years out of date upon arrival. Any response would take another 4 years to return. A conversation with an 8-year round-trip delay is not really a conversation at all. It is an exchange of historical documents. A colony at Tau Ceti, 12 light-years distant, would face a 24-year round-trip delay. A colony at the far side of the galaxy, 50,000 light-years distant, would face delays of 100,000 years. Any message sent today would arrive 50,000 years from now, when the recipient civilization, if it still exists, will have evolved in ways we cannot possibly predict. Any reply would arrive 50,000 years after that, 100,000 years from now when Earth itself may no longer harbour anything recognizable as human civilization. Under these conditions, the very concept of a unified civilization becomes questionable. What does it mean for two societies to share a culture when communication between them requires generational timescales? What does it mean for them to share a government when no decision can be transmitted and acknowledged faster than the light travel time between them? What does it mean for them to share an identity when each exists in a permanent informational past relative to the other? The science fiction dream of a galactic empire, with instantaneous communication and rapid travel between far-flung worlds, founders on this rock of relativistic reality. The speed of light is not merely a barrier to motion, it is a barrier to coordination, to simultaneity, to any form of real-time interaction across cosmic distances. The galaxy is not merely large, it is temporally shattered, a vast archipelago of causally isolated islands separated by gulfs of time as well as space. And yet within this seemingly bleak picture lies a strange form of hope. The same physics that fragments the cosmos also offers a form of temporal liberation. A traveller departing Earth today at high relativistic velocity could witness the far future of the universe without waiting for it. The journey would be one way, the sacrifice would be permanent, but the opportunity would be genuine. Imagine accelerating at 1 gravity, a comfortable acceleration that would feel like normal Earth gravity to the passengers, and maintaining that acceleration for 30 years of ship time. Relativity tells us that such a journey would carry the traveller approximately 26,000 light-years, placing them roughly halfway across the galaxy. The Earth they left behind would have aged tens of thousands of years. Every person they knew would be gone. Every institution they recognised would have transformed or vanished. But they themselves would have experienced only 3 decades of life. Continue the acceleration for 40 years of ship time, and the traveller reaches distances of 500,000 light-years, well beyond the Milky Way itself, into intergalactic space where the great spiral of home shrinks to a mere smudge of light. The Earth left behind is now hundreds of thousands of years in the traveller's past, unimaginably transformed or perhaps no longer bearing life at all. Continue for 50 years of ship time, and the traveller has crossed distances of tens of millions of light-years. The local group of galaxies recedes. The great clusters and superclusters of the cosmic web become visible structures. The universe unfolds in all its vast architecture. And still the traveller ages only at the ordinary human rate, experiencing the ordinary succession of days and years, while cosmic epochs unspool in the reference frame they departed. The mathematics permits a human being, within a single biological lifetime, to witness the deep future of the cosmos. 100 years of ship time at 1 gravity acceleration would carry a traveller so far that the universe itself would have aged by trillions of years. Stars would have burned out, galaxies would have dimmed. The cosmos would have entered its long twilight, trending toward the cold equilibrium of maximum entropy. The traveller would step out of their vessel into a universe profoundly different from the one they left, a universe where the conditions that permitted life as we know it have long since faded. This is not travel to another place, it is travel to another era. The relativistic starship is not merely a vehicle of spatial transport, it is a time machine, moving forward through history at an accelerated rate relative to the universe it traverses. The passengers cannot return to their own time, they cannot send messages to their past, but they can reach a future that would otherwise require them to wait through billions of years of cosmic evolution. We stand, then, at a curious juncture in our understanding of time. The second that began as a practical subdivision of the day, refined through pendulums and quartz and cesium atoms into the most precise measurement humanity has ever achieved, turns out to be irrevocably local. It applies with perfect validity to the immediate vicinity of the clock that defines it, but it cannot be exported unchanged to other locations, other velocities, other gravitational environments. Every clock keeps its own time, measuring the proper interval along its own world line through the 4-dimensional geometry of space-time. This localization is not a defect in our measurements or a limitation of our technology. It is a fundamental feature of reality. Space-time is not a stage on which events occur against a backdrop of universal time. Space-time is the fabric itself, and that fabric can be stretched and curved in ways that make temporal comparisons between distant events inherently ambiguous. The question of whether 2 events are simultaneous has no absolute answer. The question of how much time elapsed between 2 events depends on the path taken between them. We perceive none of this in daily life because we spend our lives in a single gravitational environment, moving at negligible fractions of the speed of light. Our clocks agree with each other because they share nearly identical conditions. Our intuitions about time are shaped by this local agreement, and we naturally extrapolate from our local experience to assume that all clocks everywhere would agree if only they were properly synchronized. This assumption is wrong. It is not merely slightly wrong, an approximation that breaks down only under extreme conditions. It is fundamentally wrong, a misunderstanding of the nature of time itself. The universe does not possess a master clock against which all events can be measured. The universe possesses only the interlocking local times of every particle, every object, every observer, each measuring its own passage through space-time, each finding slightly different answers depending on its own unique path. The cesium atom in the atomic clock on your wall vibrates 9,192,631,770 times with each passing second. This is true. This is precisely measured. This is the foundation of our timekeeping. But the second thus defined is your second, measured along your world line, applicable to your immediate vicinity. Somewhere else in the universe, another cesium atom is vibrating at the same intrinsic rate, but its seconds are not your seconds. Its time is not your time. The gulf between you may be too small to measure with any practical instrument, or it may be large enough to span centuries for each second you experience. You're embedded in a single moment, a single slice of space-time, experiencing time at a single rate determined by your gravitational environment and your state of motion. But that moment is not universal. That slice does not extend unchanged across the cosmos. You exist in a bubble of a local time, connected to other bubbles by the mathematical relationships of relativity, but never fully coincident with them. The recognition of this truth transforms how we must understand our place in the cosmos. We are not observers standing outside of time, watching the universe unfold against a neutral temporal backdrop. We are participants embedded within the fabric of space-time itself, each of us carrying our own local clock, each of us experiencing a private flow of duration that connects to every other flow through the geometry of the universe, but never fully merges with any of them. The isolation is subtle but absolute. You cannot step outside your world line to compare your time directly with someone else's. You can only exchange signals, each signal travelling at the speed of light, each signal carrying information about what time it was at the sender's location when it departed. By the time the signal arrives, that moment has passed. The sender has moved forward along their own world line. You have moved forward along yours. The comparison you make is always retrospective, always mediated by the finite speed of light, always complicated by whatever relative motion and gravitational differences exist between you. Consider what this means for any attempt to coordinate activity across cosmic distances. If humanity establishes a colony on a planet orbiting Proxima Centauri, 4 light-years away, the colonists on Earth can never agree on what time it is right now at the other location. A message sent from Earth takes 4 years to arrive. A reply takes another 4 years to return. When the reply arrives, it describes conditions that existed 8 years ago from Earth's perspective. But from the colonists' perspective, their reply was sent immediately upon receiving Earth's message. Each party experiences continuous time, but the 2 time streams run in parallel without ever intersecting at a shared present moment. The colonists might transmit news of a discovery. Earth receives this news 4 years later and sends congratulations. The colonists receive the congratulations 4 years after that. By the time they receive it, they have lived 8 years since making the discovery. From their perspective, Earth is congratulating them on something that happened nearly a decade ago. From Earth's perspective, the discovery only happened 4 years ago when the news arrived. Both perspectives are correct. Neither perspective is privileged. The events themselves are fixed points in space-time, but the temporal relationships between those events depend entirely on who is asking and from where. This becomes even more disorienting when we consider what simultaneity actually means across cosmic distances. On Earth, we have a strong intuitive sense that events happening right now are happening right now everywhere. When you look at your watch and see that it reads 3:14 p.m, you naturally assume that it is also 3:14 p.m. right now, on the surface of Mars, on the moons of Jupiter, in the core of the Sun. But relativity reveals that the phrase right now has no absolute meaning for spatially separated events. Different observers, moving at different velocities, will disagree about which distant events are simultaneous with which local events. An observer moving past you at high speed might judge that your 3:14 p.m. is simultaneous with a moment on Mars that you would judge to be in the future. Another observer moving in the opposite direction might judge that your 3:14 p.m. is simultaneous with a moment on Mars that you would judge to be in the past. The disagreement is not a matter of confusion or imprecise measurement. It is a fundamental feature of the relativistic structure of space-time. Simultaneity is relative, just as time intervals and spatial distances are relative. Only certain combinations of space and time intervals remain the same for all observers. The individual components can be mixed and redistributed depending on the observer's state of motion. This revelation carries profound implications for our understanding of existence itself. If there is no universal now, no cosmic present moment that extends across all of space, then what does it mean for the universe to exist at this moment? In the classical picture, the universe exists in a succession of 3-dimensional slices, each slice representing the state of all matter and energy at a single instant of universal time. The past slices are gone, preserved only in memory and record. The future slices do not yet exist, waiting to be created by the unfolding of physical law. The present slice is the only one that truly exists, the knife edge of reality separating what has been from what will be. But relativity dissolves this picture. If different observers disagree about which events are simultaneous, they disagree about which events belong to the same three-dimensional slice of now. Your present moment might include events that I would classify as past or future. My present moment might include events that you would classify differently. There is no objective fact about which events are happening now across the universe. The three-dimensional slice that you experience as the present exists only from your particular perspective, defined by your particular state of motion. Some physicists and philosophers have drawn from this the conclusion that past, present, and future are equally real. This view, sometimes called eternalism or the block universe, holds that the entire four-dimensional structure of space-time exists as a completed whole. Events do not come into being as the present moment reaches them. They simply exist at their locations in the four-dimensional block. Your experience of the present as special, as uniquely real, is a property of your consciousness, not a property of the universe. From the perspective of the block universe, your birth is just as real as your death, both fixed forever at their respective locations in the four-dimensional structure. Nothing ever truly passes away because everything simply occupies its eternal position in the block. This is a strange and disquieting picture of reality, and not all physicists accept it. The debate over the ontological status of time remains unresolved, tangled with questions about consciousness, causation, and the ultimate structure of physical law. But the relativistic framework that generates these questions is not in dispute. Time dilation is real. The relativity of simultaneity is real. The localization of temporal measurements to individual world lines is real. Whatever philosophical conclusions we draw, we must draw them from premises that have been tested to extraordinary precision. And so, we arrive at the deepest irony of our timekeeping achievements. We have built clocks of almost inconceivable precision, capable of detecting variations in the flow of time smaller than any phenomenon we encounter in daily life. These clocks have confirmed, again and again, that time is exactly as strange as Einstein predicted, and in confirming this strangeness, they have revealed that our entire project of building better clocks, of defining the second with ever greater precision, is in some sense a local endeavour. The perfect clock keeps perfect time only for itself. Export it to another location, another velocity, another gravitational environment, and its perfection becomes irrelevant. It will still keep perfect time, but its time will no longer be your time. The muon that lives for 2 microseconds in its own frame and 20 microseconds in the laboratory frame experiences no contradiction. From the muon's perspective, it lives exactly as long as muons always live. The time dilation that extends its apparent lifetime in the laboratory frame is not something the muon experiences. The muon simply exists, vibrates, decays, all within the normal time frame that muons have always known. The strangeness appears only when we try to compare the muon's time to ours, when we try to impose our second onto a particle moving at 99% of the speed of light. The muon keeps its own time, we keep ours. The relationship between them is governed by the Lorentz transformations, by the geometry of space-time, by the fundamental structure of the universe. But neither time is more real than the other. Neither clock is more correct. This equality of perspectives extends across every scale the universe contains. The cesium atoms in our atomic clocks vibrate at the same intrinsic rate as cesium atoms anywhere in the cosmos. But a cesium atom falling toward a black hole experiences time differently than a cesium atom on Earth's surface. A cesium atom on a spacecraft travelling at relativistic velocities experiences time differently than a cesium atom stationary in the laboratory. Each atom keeps perfect time according to its own experience. Each atom's seconds are locally valid. But the seconds themselves are not interchangeable. They cannot be added together, cannot be averaged, cannot be reconciled into a single universal count. We live, then, in a universe without a master clock. The question of how much time has passed since the Big Bang has no precise answer, because there is no absolute reference frame from which to measure. Cosmologists typically define cosmic time as the proper time experienced by an observer at rest, with respect to the cosmic microwave background radiation, the faint afterglow of the early universe that fills all of space. This provides a useful reference, a way to define a shared temporal coordinate for discussions of cosmic evolution. But it is a convention, not a fundamental truth. Other observers, moving at high velocities relative to the cosmic microwave background, would measure different elapsed times since the beginning. The universe does not care about our conventions. It simply provides the mathematical framework within which all measurements must be made. The practical implications of this framework are already woven into the technologies we depend on every day. The GPS satellites orbiting overhead carry atomic clocks that run slightly faster than identical clocks on Earth's surface, their greater distance from Earth's centre placing them in a region of weaker space-time curvature. Without corrections for this gravitational time dilation, and for the time dilation caused by their orbital velocity, the GPS system would accumulate errors of roughly 10 kilometers per day. Your smartphone's ability to locate you within a few meters depends on engineers taking seriously the lessons of general relativity, building the strangeness of time directly into the software that processes satellite signals. Every time you request directions or summon a rideshare, you're relying on clocks that acknowledge their own locality, that compensate for the fact that time flows differently at different altitudes above Earth's surface. Future technologies will require even more sophisticated accounting for temporal variations. The proposed square-kilometre array, a radio telescope that will span 2 continents, will require timing precision across thousands of kilometres. The signals from individual antenna stations must be combined with nanosecond accuracy to construct coherent images of distant cosmic sources. Achieving this precision will require careful attention to the gravitational time differences between stations at different elevations, the timing effects of Earth's rotation and orbital motion, the subtle influences of atmospheric variations on signal propagation. The telescope will not merely observe the universe, it will exemplify the universe's strange relationship with time, its construction demanding that engineers honour the local nature of temporal measurement. Deep space missions present similar challenges. A probe travelling to the outer solar system experiences time differently than ground controllers on Earth. The differences are tiny, measured in microseconds per day, but they accumulate over the years-long duration of interplanetary missions. The onboard clocks drift relative to Earth clocks, and this drift must be accounted for when navigating to distant targets, when coordinating observations, when interpreting scientific data. The probe lives in its own time stream, connected to Earth's time stream by radio signals travelling at the speed of light. The two streams never quite synchronised, always slightly out of phase. The most ambitious proposed mission in human history would transform these subtle effects into the defining feature of the journey. A spacecraft travelling to another star at a significant fraction of the speed of light would experience time so differently from Earth that the crew and their civilization would effectively part ways forever. The crew might return to find that everyone they knew had died centuries ago, or they might never return at all, continuing outward into a universe growing ever more alien as the cosmic acceleration carries distant galaxies beyond the reach of any signal. The time dilation that allows such a journey also creates an unbridgeable gulf, a one-way passage into a future that the rest of humanity will experience second by second, while the travellers skip across decades like stones across water. This is the price the universe demands for rapid transit through space. Exile through time. The traveller gains access to distant destinations, but loses access to the present from which they departed. The trade cannot be avoided or negotiated. It is built into the geometry of space-time itself, a necessary consequence of the finite speed of light and the impossibility of absolute simultaneity. Every second saved in ship time is a second lost forever in the timeline of home, and yet humanity looks upward. We build telescopes to observe galaxies whose light departed billions of years before our planet formed. We send probes to the edges of the solar system, knowing that the signals we receive describe conditions that existed hours before we received them. We dream of missions to other stars, missions that would require generations or relativistic velocities or both. The strangeness of time does not deter us. If anything, it fascinates us, drawing us deeper into questions about the nature of existence, the meaning of duration, the relationship between observer and observed. The second on your watch, that fundamental unit you have used to measure your entire life, turns out to be a window into the deeper structures of reality. It is not merely a convenient subdivision of the day, not merely a practical tool for scheduling meetings and catching trains. It is a measurement of your personal passage through the four-dimensional geometry of space-time, a reading from a clock that only you carry, a count that only you can verify. Other clocks in other places keep their own counts, their own seconds, their own time. The universe weaves these countless local times together through the equations of relativity, but it never demands that they agree. It permits, even requires, their divergence. You are living right now at the intersection of countless time streams. The cesium atoms defining your second are vibrating in their own local time. The muons passing through your body from cosmic ray impacts are living out their brief lives in a time dilated by their tremendous velocities. The satellites overhead are experiencing time slightly faster than you, their clocks running ahead by microseconds each day. The dense core of Earth beneath your feet is experiencing time slightly slower than you, its clocks running behind by an even smaller margin. The distant quasars whose light reaches your eyes tonight emitted that light when time flowed at rates determined by their own local conditions, rates that cannot be simply compared to yours. You're surrounded by temporal diversity, embedded in a web of different time rates that you cannot perceive directly, but that modern physics has mapped with extraordinary precision. The second is not a constant. It is a relationship. It is your relationship to the space-time you inhabit, to the gravitational field in which you live, to the velocity at which you move. Change any of these conditions and your seconds will change with them, not because your clock is broken, but because the fabric of reality is more flexible, more responsive, more strange than everyday intuition suggests. We began by asking what a second really is. We traced the answer from the ancient Egyptians dividing days and nights into 12 hours each, through the medieval innovations that made clocks small enough to carry, through the pendulums and quartz crystals that made precision portable, through the atomic transitions that finally gave us a definition independent of Earth's inconstant rotation. We discovered that the second, once divorced from celestial motion, became anchored to something deeper, the fundamental frequencies of matter itself, the quantum vibrations of cesium atoms that tick away with stupefying regularity. This was supposed to be the end of the story, the final answer, the ultimate definition that would serve for all time. But the universe had other ideas. The same physics that gave us atomic clocks also gave us relativity. The same 20th century that produced the cesium standard also produced the equations showing that time itself is variable, that clocks run at different rates depending on where they are and how they move, that the second is not a universal constant but a local measurement. The harder we tried to pin down the meaning of a second, the more clearly we saw that seconds mean different things in different places. This is not a failure of physics. This is the triumph of physics. We have learned something true about the universe, something strange and beautiful and deeply counterintuitive. We have learned that time is not a river flowing uniformly past all observers. Time is more like a vast web of interlocking threads, each thread keeping its own pace, each thread connected to every other through the mathematical structure of space-time but never fully synchronized with any. Your thread is your world line. Your seconds are measured along your thread. They are real and valid and perfectly precise. They are also utterly local, applicable to your thread and no other. Somewhere in the universe, a particle is experiencing what it considers to be 1 second. That second might contain decades of your time, or fractions of your microseconds. Both measurements are correct. Both clocks are accurate. The universe contains room for both, for all, for the infinite variety of temporal experience that arises from the infinite variety of world lines threading through space-time. The clock on your wall ticks. The cesium atoms in Standards laboratories around the world vibrate. The GPS satellites transmit their timing signals. The pulsars spin. The muons decay. The black holes curve space-time until time itself slows to a crawl. All of these processes are happening now, whatever now means, across distances where simultaneity loses its objective footing. All of them are measuring time, counting seconds, keeping track of duration. None of them are wrong. All of them are local. The universe has no master clock. It has only the myriad local clocks of every particle, every field, every region of curved space-time, each keeping its own time with perfect fidelity, each disagreeing with every other by amounts large or small. You exist within this fabric. Every second you experience is a second measured along your world line, a second defined by the conditions of your local environment, a second that connects you to the rest of the universe through the mathematics of relativity, but never quite matches any second measured anywhere else. The precision of modern atomic clocks has not overcome this localization. It has revealed it, clarified it, made it measurable. We can now detect time differences so small that they were once considered purely theoretical. We have confirmed, beyond any reasonable doubt, that Einstein was right, that Minkowski was right, that the space-time framework they bequeathed us accurately describes the temporal structure of the cosmos. And so we return to the beginning, to the simple question of what time it is. The answer depends on where you are, how you are moving, what gravitational field you inhabit. There is no absolute answer, no cosmic timekeeper, no universal now that extends across all of space. There is only your now, your second, your clock, your world line threading through the four-dimensional structure of space-time. You are keeping time for yourself. Everyone else is doing the same. The universe accommodates all of you, all of us, without contradiction, because its geometry is large enough to contain every possible path, every possible rate of time, every possible answer to the question of how long a second lasts. The stars will continue to burn for billions of years in their own proper time. Civilizations may rise and fall. Species may emerge and vanish. Black holes will grow and eventually evaporate, their event horizons shrinking over timescales so vast that even their internal seconds will number in numbers beyond human comprehension. Throughout all of this, time will continue to flow, not uniformly, not universally but locally everywhere, measured by every particle that experiences duration, defined anew at every point in the cosmos. This is what your second is. It is a local truth, a personal measurement, a window into your unique path through the fabric of reality. It is defined by atomic transitions that occur billions of times in what feels to you like a single heartbeat. It is dilated and contracted by the conditions of your environment. It connects you to every other timekeeper in the cosmos through equations that humanity discovered barely a century ago. And it reveals, with every tick, that the universe is stranger and more beautiful than any intuition could have prepared us to expect. The cesium atoms vibrate, the seconds pass. But now you know that those seconds are yours, measured along your world line, valid for your location, part of a vast and interconnected web of local times that spans the entire universe. Time is not a river. It is an ocean, with currents flowing at different speeds in different places, with depths where seconds stretch toward infinity and surfaces where they flash past in instants. You swim through this ocean every moment of your life, measuring the flow with clocks that have become almost impossibly precise, yet finding always that the flow is local, that the current is your current, that the time you measure is, in the end, only your time. The stars are not impossibly distant. They merely wait for us to develop the means to reach them and to accept the temporal price the journey requires. The seconds are not impossibly brief. They merely vibrate at frequencies too fast for conscious perception, each one containing multitudes of atomic oscillations that define its length with extraordinary precision. The universe is not impossibly strange. It merely operates according to rules that differ from everyday intuition, rules that modern physics has decoded with painstaking care over the past 100 years. Your watch ticks, another second passes. But now you understand what that second contains. The vibrations of cesium, the legacy of Einstein, the geometry of space-time, the beautiful and inescapable locality of all temporal measurement. The word second has not changed. Your relationship to that word has changed forever. It will never again be a simple unit, a mere subdivision of the hour, a practical convenience for daily life. It will always carry with it the weight of everything you now know about time's strange and mutable nature. This is the gift that physics offers, not certainty, but clarity, not simplicity, but depth, not answers that close questions, but answers that open new questions, deeper questions, questions that may take centuries or millennia to resolve. The second, that humble unit we use to measure our lives, turns out to be a doorway into the most fundamental questions about the nature of reality. Walk through that doorway, and you find yourself in a universe far more interesting than the one you imagined before. 1 second is not a universal unit. It never was. The universe does not require one. The universe requires only that each observer, each particle, each clock keeps faithful track of its own local time. And this the universe provides, with a mathematical elegance that still astonishes those who contemplate it. The fabric of space-time curves and stretches. The seconds dilate and contract. Time flows differently everywhere, and through it all, the cesium atoms vibrate, The muons decay, the stars burn, the black holes swallow light, each keeping its own perfect time, each measuring its own seconds, each part of a cosmos that has no master clock but infinite room for every clock that ever existed or ever will.